Industrial Automation, A Guide for Controls Engineers by Hamed Adefuwa. Feel free to get in touch on my email, hamed@hamed.engineer. Introduction. Industrial automation is complex. It's not just about wiring a panel or making a machine move. It's about designing safe, reliable, and standards-compliant control systems that work seamlessly within modern industrial environments. As a controls engineer, you are expected to navigate a world of safety regulations, functional safety standards, control architectures, and system integration challenges, all while keeping machines running and production targets met. From understanding performance level, PL and safety integrity level, SIL requirements, to selecting the right PLC or designing a motion control system, there's a lot to get right, and a lot that can go wrong if done poorly. This book is my attempt to gather all those critical pieces in one place. Originally, I started writing this as a personal reference, something I could turn to when I needed to remind myself of how to properly approach a safety-rated system, which standards apply to which type of machinery, or how to structure a system to meet both functional and safety requirements. Over time, I realized that if I need this guide, others probably do too, so I've decided to share it publicly. Unlike textbooks that focus on theory or narrow application manuals, this guide is about real-world system design. It covers the principles and standards that shape industrial control systems, from concept to commissioning. Whether you're designing a new system from scratch, upgrading an old one, or working on a complex machine with multi-axis motion and advanced safety systems, this book provides practical guidance. It explains how to apply safety standards such as ISO 13849, IEC 62061, IEC 61508, and EN 60204-1. It helps you design control systems that meet required performance levels, PL, and SIL ratings based on risk assessments. It walks you through selecting the right hardware architecture for PLC, motion, and safety integration. It details the integration of safety functions like emergency stops, safety light curtains, and safe motion, STO, SS1, etc. It introduces modern control system design principles, including distributed I/O, safety over networks, and Industry 4.0 integration. It clarifies functional safety concepts and ensures system compliance with regional and international machinery directives and standards, such as EN 60204-1, Machinery Directive 2006/42/EC, and NFPA 79. This book is for engineers who are responsible for designing and specifying automation systems, not just the how-to of wiring or programming, but the why and what of proper system design, including safety, reliability, and maintainability. Whether you're an experienced controls engineer who needs a reference on complex safety integration or someone new to designing systems from the ground up, this book is for you. My goal is simple: to create a practical reference guide for serious controls engineering, something that I wish had existed when I first started working on complex automation projects. If that's what you're looking for, let's get started. 3 Foundations of Industrial Automation. 3.01. What is industrial automation? Industrial automation is the application of advanced control technologies to manage industrial machinery and processes, typically with minimal human intervention. It encompasses the use of programmable logic controllers, PLCs, distributed control systems, DCS, supervisory control and data acquisition, SCADA, robotics, and various sensors and actuators. Automation serves as the backbone of modern manufacturing and processing industries, improving productivity, ensuring consistent quality, and enhancing safety and reliability. At its core, industrial automation replaces or augments repetitive, hazardous, or highly precise human tasks with machinery and control systems. Initially, automation involved straightforward control strategies, basic start-stop logic, relay-based control panels, or simple motor control applications. Today, automation has evolved into complex, intelligent, interconnected systems capable of real-time decision-making, predictive analytics, and adaptive process control. 3.0.1.1 Current state of industrial automation. Currently, industrial automation is widely deployed, but varies significantly in complexity across different industries and facilities. Most modern factories employ a combination of automation technologies, typically involving the following: programmable logic controllers, PLCs. PLCs are the central elements of factory floor control handling logic decisions based on sensor inputs, executing sequential operations, and communicating with higher level systems. Distributed control systems, DCS, predominantly found in process industries, oil and gas, chemicals, pharmaceuticals. DCS provide integrated control and data management for complex continuous processes. Supervisory control and data acquisition, SCADA. SCADA systems facilitate remote monitoring and control, alarm management, and data logging across geographically dispersed equipment, essential for infrastructure and utility sectors. Robotics. Industrial robots have become commonplace, especially in sectors like automotive, electronics, and packaging. They range from simple pick-and-place robots to advanced collaborative robots, cobots, designed for safe interaction with humans. Vision and inspection systems. Machine vision systems offer precise, high-speed quality inspections, defect detection, and guidance for robots or machinery, replacing human visual inspections with higher accuracy and consistency. Industrial networking and connectivity. Networks such as Ethernet/IP, Profinet, EtherCAT, OPC-UA, and IO-Link facilitate rapid, secure data transfer between sensors, controllers, and enterprise-level systems like manufacturing execution systems, MES, and enterprise resource planning, ERP. Despite widespread implementation, many factories today still rely heavily on traditional or legacy systems, creating challenges in integration, cybersecurity, and effective use of available data. As a result, the full potential of automation, particularly the capabilities enabled by Industry 4.0 technologies, is often not fully realized in practice. 3.0.1.2 How factories currently implement automation. Many factories currently implement automation incrementally, often retrofitting newer systems onto existing infrastructure. Common practical scenarios include standalone automated machines, machines automated individually, often lacking integration with other plant systems, limiting data exchange and real-time optimization opportunities. Partial automation, facilities that automate specific tasks or areas, e.g., robotic assembly lines, automated packaging, or palletizing stations, while manual tasks still dominate other processes. Reactive maintenance and troubleshooting. Many factories still rely on reactive maintenance strategies rather than predictive or condition-based maintenance due to limited data visibility and analytics capability, limited connectivity and data integration. Older automation equipment may not support modern communication standards, causing fragmented data collection and inefficient operation. Integration typically occurs through gateways or middleware, complicating the automation landscape. 3.0.1.3 The ideal implementation of automation. Optimally, factories should adopt a more holistic approach to automation, one that aligns with Industry 4.0 and smart manufacturing principles. Best practice implementations include fully integrated control systems, seamless integration of PLCs, HMIs, SCADA, MES, and ERP systems into a unified architecture, allowing real-time data exchange, system-wide optimization, and streamlined operations. Smart sensors and edge computing. Deployment of advanced sensors with integrated intelligence, IO-Link sensors, condition monitoring sensors, and edge computing devices to pre-process data locally and enable real-time decision-making. Predictive and condition-based maintenance. Utilization of AI-driven analytics for predicting machine failure, scheduling maintenance proactively, and minimizing downtime and maintenance costs. Secure industrial networks, IEC 62443 compliance. Modern factories must incorporate robust cybersecurity practices into automation infrastructure with network segmentation, secure protocols, and strict access controls. Standardization and modularity, ISA 88, ISA 95. Adoption of modular, scalable architectures and standardized software approaches, such as ISA 88 for batch processes and ISA 95 for enterprise integration, enabling flexible manufacturing and rapid deployment of new product configurations. 3.0.1.4 Future direction of industrial automation. Automation is rapidly moving towards a more autonomous, intelligent paradigm shaped by advancements in artificial intelligence and machine learning. AI-powered control algorithms and predictive models will increasingly handle complex decision-making and adaptive process optimization. Collaborative and autonomous robots. Robots and cobots will increasingly operate alongside humans with advanced safety and intuitive interfaces, enhancing efficiency and flexibility in manufacturing. Digital twins. The rise of digital twin technology, virtual replicas of physical assets, will enable more accurate simulation, optimization, and predictive analysis of systems before physical implementation. Cloud and edge. Integration, hybrid architectures, leveraging edge computing for low latency tasks, and cloud computing for big data analytics will become commonplace, providing both speed and scalability. Sustainability and energy management. Automation will increasingly focus on sustainable manufacturing practices, including optimized energy use, waste minimization, and carbon footprint reduction through intelligent monitoring and real-time control. Industrial automation encompasses far more than just machinery control. It represents a fundamental shift in manufacturing towards integrated, data-driven, adaptive, and intelligent operations. Controls engineers today must understand the breadth of automation technologies and actively participate in the transition towards smarter, fully connected factories, taking care to design systems that are not only technologically advanced, but secure, flexible, and aligned with future industrial demands. Role of the controls engineer. The controls engineer plays a pivotal role in industrial automation, uniquely positioned at the intersection of multiple engineering disciplines, including electrical engineering, mechanical systems, software development, and safety engineering. This interdisciplinary skill set enables them to conceptualize, design, and maintain sophisticated industrial automation systems that meet both operational and regulatory requirements. Controls engineers are expected to have deep expertise in hardware and software aspects of automation systems, possess comprehensive knowledge of applicable industry standards and regulations, and remain proficient in current and emerging technologies. 4.1 Key responsibilities of the controls engineer. 4.1.1 Designing control systems. Designing robust control systems requires selecting and integrating appropriate hardware and software components to achieve reliable and efficient machine operation. Key tasks include hardware selection, architecture development, and control loop design. 4.1.2 Hardware selection. Selecting the correct hardware is crucial for ensuring the performance, safety, and reliability of automated systems. Controls engineers must systematically evaluate the operational requirements of each application to choose components that accurately match performance needs, regulatory standards, and future scalability considerations. When selecting programmable logic controllers, PLCs, controls engineers carefully evaluate the number and types of inputs and outputs required, processing speeds, scan time requirements, memory capacity, supported communication protocols such as Ethernet IP, Profinet, or EtherCAT, and expansion capability to accommodate future system growth. For safety-critical applications, safety-rated PLCs compliant with functional safety standards like ISO 13849 and IEC 62061 should be used. These PLCs provide additional diagnostics and certified fault tolerance required to achieve defined safety integrity levels or performance levels. For applications involving high-speed motion or robotics, specialized PLCs offering deterministic and real-time motion control capabilities become essential. When selecting human-machine interfaces, HMIs, engineers must ensure interfaces are intuitive, responsive, and clearly structured. Considerations include screen size and resolution, ease of navigation, communication protocol compatibility, and robust security features such as secure authentication. Additionally, HMIs must support the effective visual representation of critical alarms, diagnostics, and real-time process data, enabling operators to rapidly identify and respond to operational conditions. Environmental considerations, such as the required IP rating for protection against dust, moisture, and harsh factory environments, must be checked alongside manufacturer specifications. Servo systems and motion control hardware selection requires detailed consideration of mechanical load inertia, torque, acceleration, speed profiles, and positional accuracy requirements. Engineers must choose appropriately rated servo motors and servo drives, ensuring compatibility with the desired real-time communication protocol, commonly EtherCAT or SERCOS, for accurate synchronization. Feedback devices like encoders or resolvers must provide sufficient resolution to meet precision requirements. Integrated safety features, such as safe torque off, STO, or safe limited speed, SLS, compliant with IEC 61800-5-2, are also important considerations, simplifying safety system design and integration. For variable frequency drives, VFDs, correct sizing relative to motor power ratings, torque, acceleration, and dynamic performance requirements is essential. Drives must support robust network integration, Profinet, Ethernet IP, for real-time monitoring and predictive maintenance. Controls engineers must also check the manufacturer's manual to confirm required clearances and cooling arrangements, ensuring sufficient heat dissipation space is provided. Choosing drives with integrated safety features such as safe torque off, STO, simplifies compliance with machine safety requirements. Selecting sensors and actuators involves matching sensor accuracy, resolution, response time, and output type, digital, analog, I/O link, to application-specific requirements. Engineers must consider environmental resilience, including IP ratings, temperature tolerance, vibration resistance, and chemical compatibility. Actuators, such as pneumatic cylinders or electric linear drives, must be chosen based on load capacity, operational duty cycle, stroke length, and positioning accuracy. Actuator and sensor selections must align clearly with PLC input-output specifications, providing predictable and reliable signals. For safety-related components, engineers must select safety-rated devices certified according to relevant UK and EU standards, including EN ISO 13849 and IEC 61496. Devices such as emergency stops, interlocks, and safety light curtains must achieve the specified performance level, PL, or safety integrity level, SIL, based on risk assessments. Diagnostic capability must be adequate to detect faults promptly, ensuring safe and reliable operation throughout the system lifecycle. Engineers should strictly follow manufacturers' recommended installation conditions to achieve the required performance levels. By systematically applying these technical considerations, careful PLC and HMI selection, precision in sizing motion components, ensuring compatibility and correct ratings of sensors and actuators, and diligent specification of safety-critical hardware, controls engineers design robust automation systems capable of reliably meeting demanding operational safety and regulatory requirements. Proper hardware selection forms a critical foundation for the overall control system architecture, enabling long-term performance, maintainability, and compliance with UK, EU, and international industry standards. 4.1.3 Control Loop Design. Effective control loop design ensures that automated systems run accurately, reliably, and efficiently. Controls engineers commonly use PID, proportional integral derivative controllers, to manage important process variables such as temperature, pressure, flow, and position. To achieve stable and precise control, engineers apply standard tuning methods, including Ziegler-Nichols, Cohen-Kuhn, or modern model-based techniques. Good PID tuning minimizes overshoot and prevents instability. In systems involving step-by-step or sequential operations, state-based logic, also known as finite state machines, is essential. Here, engineers clearly define specific operational states such as idle, start, run, fault, and stop, and describe exact conditions for transitioning between these states. This structured approach makes system behavior predictable, easier to validate, and simpler to troubleshoot. Sequential function charts, SFC, provide another useful tool for managing sequences and batch processes. SFC diagrams visually represent each step of a process, clearly showing how the system moves from one step to the next based on logical conditions. Because SFCs offer an intuitive representation of sequential logic, they help operators quickly identify current states, understand process flows, and diagnose issues efficiently. For more complicated systems involving multiple interacting variables or nonlinear processes, engineers often implement advanced control methods such as Model Predictive Control (MPC), Adaptive Control, or Fuzzy Logic. MPC, for instance, uses predictive models to anticipate process changes and proactively adjust controls, improving responsiveness and stability. Adaptive Control automatically adjusts parameters in real time to handle changing conditions, ensuring consistent performance. Finally, robust control loop design includes built-in fault handling and diagnostics. Engineers incorporate checks to detect sensor errors, equipment faults, or unexpected process behavior. These diagnostics can trigger clear, actionable alarm messages displayed through HMI and SCADA systems, enabling operators to quickly respond and minimize downtime. In summary, controls engineers achieve effective loop control by carefully selecting and tuning PID controllers, clearly defining state-based logic and sequential flows, implementing advanced control techniques when necessary, and embedding thorough diagnostics to ensure reliability, maintainability, and stable performance of automated systems. 4.1.4 Software. A controls engineer is responsible for the full software development lifecycle of automation and control systems, from initial design and programming through optimization and long-term maintenance. This role involves selecting and implementing appropriate IEC 61131-3 PLC programming languages according to the requirements and complexity of the control tasks. Ladder logic, LD, due to its intuitive graphical representation, is widely used for discrete machine logic, safety-critical circuits, and traditional relay-based replacement tasks, offering clear visibility and ease of troubleshooting. For tasks involving complex algorithms, advanced calculations, or intensive data manipulation, structured text, ST, known as structured control language, SCL, in Siemens systems, is preferred. Its modular structure facilitates reusable, maintainable code and supports sophisticated control algorithms like adaptive PID loops, data filtering, and statistical analysis. Function block diagrams, FBD, are commonly utilized in process control and continuous operations, where their graphical representation of signal flows and mathematical functions greatly enhances understanding and troubleshooting. Sequential function charts, SFC, provide clear visualization of sequential machine states and transitions, ideal for batch processing, complex assembly lines, or multi-stage operations. By carefully selecting and combining these languages, the controls engineer ensures both readability for operators and maintenance teams, as well as efficient, robust control logic that scales effectively across various tasks. Beyond language selection, controls engineers must develop modular and structured software architectures that comply with international standards such as ISA 88 and ISA 95. ISA 88 principles guide engineers in creating reusable software modules or function blocks representing common plant components, motors, valves, sensors, and process sequences. This structured approach greatly reduces engineering time, improves consistency across automation projects, simplifies maintenance, and allows easy scalability. ISA 95 further ensures seamless integration of control systems with higher-level enterprise systems like manufacturing execution systems, MES, and enterprise resource planning, ERP, providing critical visibility into real-time production status, quality monitoring, and resource planning. A critical responsibility of controls engineers is embedding robust diagnostics and error handling routines within the PLC software. Effective diagnostics logic helps quickly identify and isolate faults, such as sensor failures, actuator malfunctions, or communication interruptions. This significantly reduces downtime by clearly indicating the root cause to operators and maintenance personnel via actionable messages displayed on HMI and SCADA systems. For example, engineers must program range checks for analog sensors, e.g., detecting a disconnected pressure sensor if its reading drops below a valid threshold, actuator feedback validation, confirming that a valve reached its commanded position, and network communication monitoring, raising alarms upon loss of critical field device communications. Properly designed diagnostics not only enhance machine reliability, but also contribute significantly to operational safety, ensuring timely and safe responses to abnormal conditions. Effective alarm management is closely related to robust diagnostics and is another crucial responsibility. Controls engineers must thoughtfully design alarms within the PLC logic, clearly categorizing them by severity, critical, warning, informational, to avoid operator overload. Critical alarms should immediately alert operators to potentially hazardous conditions or system faults requiring immediate intervention, such as emergency stops, safety system failures, or critical sensor faults. Warning alarms indicate conditions that require attention, but pose no immediate danger, such as gradual pressure loss or temperature deviations. Informational alarms provide non-urgent updates about system status or maintenance needs. Engineers must follow ISA-18.2 guidelines to avoid alarm flooding, ensuring alarms are clear, concise, and actionable, preventing operator fatigue and enhancing safety and efficiency. Additionally, controls engineers must ensure efficient code optimization and resource management within PLC software. Poorly optimized software can lead to slow scan times, delayed system responses, and unreliable machine performance, especially in high-speed or safety-critical applications. Controls engineers should implement efficient, structured, and modular software solutions, carefully managing memory usage, reducing unnecessary computations during PLC cycles, and optimizing communication logic to maintain fast and deterministic scan cycles. This ensures responsive control systems, which are critical for accurate motion control, timely safety responses, and reliable real-time operations. Finally, controls engineers play a pivotal role in data integration and analytics. They design and implement systems that provide real-time data collection, historical process tracking, and advanced analytics capabilities. Engineers must choose appropriate communication protocols, e.g. OPC UA, MQTT, Ethernet IP, to reliably transmit PLC-generated data to higher-level SCADA, MES, or cloud analytics platforms. They facilitate predictive maintenance by integrating sensor data such as vibration, temperature, and electrical signals into analytics platforms that predict machine failures before they occur. Furthermore, they ensure data integrity and cybersecurity following standards such as IEC 62443 to protect critical industrial data from unauthorized access, modification, or compromise. In summary, a controls engineer holds broad responsibilities, from carefully choosing programming languages and developing structured modular software compliant with standards like ISA 88 and ISA 95, through implementing robust diagnostic logic, efficient alarm management, optimized code structure, and seamless data integration with advanced analytics platforms. The engineer's role ensures not only the technical reliability and operational efficiency of automation systems, but also their long-term safety, maintainability, and strategic value within modern industrial manufacturing environments. 4.2 Electrical design. While electricians, panel builders, and installation contractors typically handle the physical construction and wiring of control panels and field installations, the controls engineer is ultimately responsible for the design and specification of the system. Proper electrical design is critical to ensure that automation systems are safe, compliant, functional, and maintainable. A well-designed control system not only adheres to UK and EU regulations, but also ensures ease of maintenance, reduces commissioning time, and prevents costly errors during build and operation. The role of the controls engineer in this context is to create detailed, standards-compliant electrical designs that guide others in building the system correctly and safely. 4.2.1 Control panel design. One of the primary responsibilities of a controls engineer is to produce detailed electrical schematics, wiring diagrams, and panel layouts that define exactly how the control system should be assembled. These designs must comply with relevant UK and European standards, notably EN 60204-1, Safety of Machinery, Electrical Equipment of Machines, IEC 61439, Low Voltage Switchgear and Control Gear Assemblies, BS 7671, IET Wiring Regulations. Although NFPA 79, Electrical Standard for Industrial Machinery, is a US standard, it is worth being aware of it when working with or exporting equipment to the US, as the expectations and code requirements differ. However, for the UK, EN 60204-1 remains the primary reference. 4.2.1.1 EN 60204-1 Safety of Machinery, Electrical Equipment of Machines. EN 60204-1 is the primary standard governing the design of electrical equipment for machinery in the UK and throughout the EU. It is essential reading for any controls engineer involved in specifying, designing, or overseeing the construction of control panels and machine wiring. The standard ensures that the electrical systems within machines are safe, reliable, and compliant with both UKCA and CE marking requirements under UK supply of machinery, safety regulations, 2008, and EU Machinery Directive 2006/42/EC. Key areas covered by EN 60204-1 include wiring practices. The standard dictates how control and power wiring should be installed, specifying cable types, conductor sizes, insulation ratings, and allowable voltage drops. It also defines color coding for conductors, e.g., green-yellow for protective earth, blue for neutral, black for AC phase, and brown for DC control circuits. Circuit protection, EN 60204-1, defines requirements for overcurrent and short circuit protection, including sizing and coordination of devices like fuses, MCBS, and MCCBS. It also specifies how to protect control circuits, ensuring that faults in one section of the system do not affect the entire machine. Isolation and switching. The standard requires proper isolation devices, such as main disconnects, often lockable isolators, and emergency stop devices. It outlines how and where isolators should be positioned to ensure that machines can be safely de-energized during maintenance. Earthing and bonding, EN 60204-1, has strict requirements for protective bonding and earthing, ensuring all exposed conductive parts are properly connected to the earth system to prevent electric shock hazards. It includes guidelines for earthing of control panels, motors, and field devices. Safety of control circuits. It outlines design principles for control circuits, including ensuring reliable operation of safety-related circuits, like interlocks and emergency stops. It also addresses how to protect circuits from accidental operation and failure. Marking and documentation. The standard requires clear identification and labeling of all wiring, terminals, devices, and panels, and mandates that comprehensive documentation, e.g., circuit diagrams, parts lists, must be provided for maintenance and troubleshooting purposes. For controls engineers, EN 60204-1 is crucial when designing control panels and specifying machine electrical systems to ensure that all equipment is safe to operate and meets legal compliance. 4.2.1.2 IEC 61439 Low Voltage Switchgear and Control Gear Assemblies. IEC 61439 is an international standard adopted in the UK as BSEN 61439 that governs the design and construction of low voltage switchgear and control gear assemblies, including industrial control panels. It applies to the physical construction and verification of the panels themselves, making it highly relevant for controls engineers when specifying panel build requirements, component selection, and layout. Key areas covered by IEC 61439 include temperature rise limits. Panels must be designed so that internal components do not exceed their rated temperatures during normal operation. Controls engineers must consider heat dissipation, ventilation, and component placement to prevent overheating. This often involves specifying panel cooling solutions, fans, heat exchangers, or derating components based on ambient conditions. Short circuit withstand ratings. Assemblies must be able to withstand fault conditions without catastrophic failure. Engineers must calculate the prospective short circuit current at the panel and ensure that the assembly, including bus bars and protective devices, is rated accordingly. This includes defining internal separation, Form 1 to Form 4, based on the application. Mechanical construction and protection. The standard details enclosure construction requirements, including material specifications, IP ratings for dust and water ingress protection, e.g. IP54, IP65, and mechanical strength to ensure the panel can withstand physical impacts. Verification and testing. IEC 61439 mandates that the assembled control panel must undergo verification to confirm compliance. This includes design verification, e.g. thermal performance, dielectric properties, and routine verification, e.g. wiring checks, functional tests, carried out by panel builders. Controls engineers are responsible for specifying that such tests are included in procurement and build contracts. For controls engineers, while they may not physically build panels, IEC 61439 defines the construction standards that their designs must adhere to, ensuring that the final product is compliant, safe, and fit for purpose. 4.2.1.3b S7671 IET wiring regulations. BS7671, also known as the IET wiring regulations, is the UK's definitive standard for electrical installations. Although its primary focus is on fixed installations in buildings, e.g. distribution boards, lighting, socket circuits, elements of BS7671 directly apply to machinery connections, particularly when machinery is permanently installed as part of a building's electrical system. Key considerations from BS7671 that affect machine design include protection against electric shock. BS7671 provides guidance on the earthing, bonding, and protective measures necessary to prevent electric shock in case of a fault. When a machine is connected to a building's electrical system, it must comply with these protective measures, which need to be incorporated into the control system design. Isolation and switching. The regulation defines how and where isolation points should be provided, which directly influences how controls engineers specify main isolators, safety relays, and emergency stops in the system. Cable sizing and selection. BS7671 gives detailed rules for current carrying capacity, voltage drop, and thermal protection of cables, which controls engineers must consider when specifying interconnections between control panels and field devices. Discrimination and coordination. Proper selection of protective devices to ensure that faults are isolated without affecting unrelated circuits, a principle that aligns with the requirements of EN 60204-1, but is addressed more broadly in BS7671. Although controls engineers focus primarily on machinery-specific standards, like EN 60204-1, elements of BS7671 must be considered when machinery interacts with the wider electrical installation, especially for larger integrated systems, machinery linked to building infrastructure, and systems where fixed wiring regulations apply. 4.2.1.4 Control Panel Design Summary. For controls engineers in the UK, a deep understanding of these key standards is essential to produce compliant, safe, and professional designs. EN 60204-1 governs how the electrical systems inside machines should be designed, including wiring, protection, and safety. IEC 61439 ensures that the control panels are physically constructed to withstand mechanical, thermal, and electrical stresses. BS7671 applies broader electrical safety and installation rules that affect how machines are connected to the site supply. NFPA 79 is the electrical standard for industrial machinery used in the United States. It governs the design, construction, and installation of electrical systems on machinery, focusing on safety, wiring, protection, and control circuits. While EN 60204-1 applies in the UK and EU, NFPA 79 is essential when designing machines for export to or use in the US market, ensuring compliance with UL and OSHA requirements. Both NFPA 79 US and EN 62004-1 UK EU cover essential areas like emergency stops, circuit protection, grounding, and labeling, but NFPA 79 aligns with US-specific practices, e.g. UL listings, NEC compliance, while EN 62004-1 aligns with CE UKCA marking and EU directives. Controls engineers must choose the correct standard depending on where the machine will be installed. While panel builders and electricians handle the physical construction and wiring, it is the controls engineer's responsibility to ensure that the designs they produce are compliant and properly specified. Poor design cannot be fixed by good installation, so upfront engineering, based on these standards, is vital for a successful automation project. Controls engineers must ensure that panel layouts consider proper separation of high and low voltage circuits, accessibility for maintenance, e.g. spacing around terminals, clear labeling and identification of all components, and wiring conforming to BSEN 81346 for structuring and designation. Ventilation and thermal management if high power devices are included. The design should be sufficiently detailed that a panel builder can assemble the panel exactly as specified without assumptions. Proper design also reduces the risk of errors that could lead to delays or unsafe equipment. 4.2.2 Component sizing and selection. The correct selection and sizing of electrical components is critical to ensuring that industrial control systems are safe, compliant with legislation, and capable of operating reliably under all foreseeable conditions. Poor component selection can lead to unsafe operation, nuisance tripping, overheating, and even catastrophic failure. Therefore, controls engineers must take responsibility for specifying components accurately and in accordance with current standards. In the UK and EU, component selection must comply with EN 60204-1, Safety of Machinery, Electrical Equipment of Machines, IEC 60947 series, Low Voltage Switchgear and Control Gear, BS 7671, IET wiring regulations, for installation-related aspects, and wider requirements of the UK Supply of Machinery, Safety Regulations, 2008, and EU Machinery Directive, 2006/42/EC, 4.2.2.1, Short Circuit Ratings and Protection. All protective devices, including miniature circuit breakers, MCBs, fuses, and molded case circuit breakers, MCCBs, must be selected to withstand and interrupt the maximum prospective fault current at the point of installation. This involves understanding the short circuit rating of the supply and ensuring that every component and cable downstream is protected accordingly. Protective devices must comply with IEC 60947-2 for circuit breakers and IEC 60269 for fuses. Engineers must ensure that devices are properly coordinated, meaning that a short circuit or overload is cleared as close to the fault as possible without affecting upstream equipment unnecessarily. Selective coordination. In control systems, it is common to have multiple levels of protection. For example, main incomer MCCB rated for high fault levels, e.g. 25 kA. Branch MCBs or fuses rated for specific circuit loads, e.g. 6 kA. Ensuring appropriate interrupting capacity and time current characteristics is essential for both safety and minimizing equipment damage during faults. 4.2.2.2 Contactors and relays. Contactors, relays, and safety relays must be rated to handle the full load current and duty cycle of the devices they control, whether motors, heaters, or solenoids. When specifying contactors, inrush currents and peak loads, such as motor starting current, must be considered. For example, AC motors require contactors rated under utilization category AC-3 for normal start-stop control and AC-4 for inching or plugging operations. IEC 60947-4-1 details these categories and provides guidance for selection. Contactors and relays must also be rated for expected switching frequency, particularly in systems with frequent start-stop sequences. Mechanical life and electrical endurance ratings must be checked to ensure long-term reliability. Safety relays must be chosen to meet functional safety standards such as ISO 1-3849-1 or IEC 62061 with sufficient performance level or SIL rating to match the risk assessment of the machine. 4.2.2.3 Overload protection. Thermal overload relays, electronic overloads, and PTC-based devices are required to protect motors and other equipment from sustained overcurrent conditions. These devices must be correctly set according to the full load current FLC of the equipment they protect, as indicated on motor nameplates or equipment datasheets. Standards such as IEC 60947-4-1 define the requirements for overload protection. Selection must also consider the class of trip, e.g. class 10-20, which defines how quickly the relay will trip under overload conditions, depending on the nature of the load, e.g. heavy-duty motor or normal fan load. Overload protection must be coordinated with short-circuit protection to ensure that all fault types are covered without nuisance tripping. 4.2.2.4 Cable sizing. Cable selection and sizing are fundamental to electrical safety and operational reliability. Engineers must calculate cable sizes based on current carrying capacity, thermal rating of conductors, voltage drop limits, especially for long cable runs, typically less than 5% for control circuits, lower for sensitive equipment. Short circuit withstand capability, ensuring cables are protected from damage in the event of a fault. Sizing should be based on installation method, e.g. enclosed in trunking, buried in conduit, which affects the current rating. References include EN 60204-1, machine internal wiring, and BS7671 for fixed installations and supply connections. Tables in British Standard 7671. Appendix 4 provide detailed current carrying capacities for different installation methods, derating factors, and voltage drop calculations. Control circuit cables, typically 0.75 square millimeters to 1.5 square millimeters, depending on load and distance, must also be considered for voltage drop and noise immunity, e.g., twisted pairs for sensitive signals. 4.2.2.5 Control power distribution. 24-volt DC control circuits are standard in modern industrial systems for powering PLC inputs, outputs, sensors, actuators, and safety devices. Controls engineers must design separate control power circuits with appropriate protection, typically using DC-rated MCBs, fuses, or electronic protection devices to isolate faults. Considerations include redundancy in control power, e.g., dual 24-volt DC supplies, for critical systems where loss of control voltage would cause unsafe conditions. Segregation of safety circuits, e.g., interlocks, light curtains, from general control circuits to ensure functional integrity. Ensuring adequate capacity for inrush currents, e.g., relay coils, solenoids, without voltage dips. Control circuits must also be protected against external faults, such as short circuits in field wiring, to prevent damage to PLC hardware. 4.2.2.6 Component derating. Components must be derated for environmental conditions, including ambient temperature. Most components are rated for 40 degrees Celsius ambient. Higher temperatures require derating or additional cooling. Altitude. At altitudes above 2,000 meters, air density decreases, affecting cooling. IEC 60204-1 and component datasheets provide derating curves. Enclosure heat rise. Panels with high internal heat dissipation, e.g. VFDs, soft starters, require airflow calculations and possibly forced cooling to prevent overheating of sensitive components. Failure to account for these factors can lead to premature component failure, reduced lifespan, or operational faults. 4.2.2.7 Compliance with CE UKCA marking and legislation. All components and assemblies must comply with CE marking, EU, and UKCA marking, UK requirements. This includes conformity with Machinery Directive 2006/42/EC, EU, and UK Supply of Machinery, Safety, Regulations 2008, Low Voltage Directive, LVD for electrical safety, EMC Directive for electromagnetic compatibility. Ensuring that only certified components are used is essential for both legal compliance and ensuring that the overall machine meets conformity assessment requirements. 4.2.2.8 Component Summary. Correct component selection and sizing is a critical responsibility of the controls engineer and foundational to building safe, reliable, and compliant automation systems. By adhering to EN 60204-1, IEC 60947, and BS 7671, controls engineers ensure that electrical designs safely handle electrical loads and fault conditions, protect equipment and personnel from electrical hazards, operate reliably under real-world conditions, fully comply with UK and EU regulatory frameworks. Good electrical design is not just about making things work, it's about ensuring they work safely, consistently, and legally for the life of the equipment. 4.2.3 Electromagnetic compatibility in control system design. Electromagnetic compatibility, EMC, is a critical aspect of control system design that must be addressed from the outset. Poor EMC practices can lead to unreliable machine operation, intermittent faults, false triggering of inputs and outputs, communication failures, and even complete system shutdowns. In the UK and EU, compliance with the EMC Directive 2014/30/EU is a legal requirement for all machinery placed on the market. As part of this, controls engineers must ensure that their system designs actively minimize electromagnetic interference, EMI, rather than treating it as an afterthought. Effective EMC management relies on understanding how and where interference is generated, how it propagates, and how sensitive equipment may be affected. It requires a coordinated approach involving correct component selection, panel design, cable management, and proper grounding techniques. 4.2.3.1 Cable shielding and earthing. Sensitive analog signals, communication lines, e.g. Ethernet, RS485 Profinet, and encoder feedback lines should always use properly shielded cables to protect against external electromagnetic noise. Shields must be connected with 360-degree bonding clamps directly to the control panel's main earth bar to ensure a continuous low-impedance path to ground. Avoid the common mistake of pigtail earthing, where the shield is connected via a single wire to earth. This introduces inductance, reducing the shield's effectiveness, especially at high frequencies. Shields should also be bonded at both ends for high-frequency interference, provided this does not introduce ground loops. Proper bonding design eliminates such issues. For analog and sensitive communication lines, it is essential that the shield's termination maintains mechanical and electrical continuity right up to the device terminal, using glands and connectors rated for EMC performance. 4.2.3.2 Separation of signal and power circuits. Keeping high voltage, high current power circuits physically separate from sensitive control and signal wiring is essential to prevent coupling of electrical noise. Motor cables, VFD output lines, and high power heating circuits should follow completely separate routes from 24V control wiring, analog signals, and communication networks. Within control panels, wiring segregation must be planned clearly in the design stage and shown in panel layout and wiring diagrams. Use separate wire ducts and cable trays, and where crossings are unavoidable, ensure cables cross at 90 degrees to minimize induced noise. For installations where long cable runs are needed, separate containment systems, such as individual metal trunking or conduit, should be used for power and signal cables. These guidelines are crucial when VFDs and servo drives are used, as their fast switching can generate significant EMI on their output lines. 4.2.3.3 Filtering and suppression. EMC filters are essential on variable frequency drives, VFDs, soft starters, and any equipment generating high frequency switching noise. These filters should be rated for both common mode and differential mode noise and be installed as close as possible to the source of interference, typically at the VFD input. Relay and contactor switching can generate electrical noise, particularly when switching inductive loads, such as motors and solenoids. RC snubber circuits should be specified across relay contacts to suppress voltage transients and reduce contact arcing. For DC circuits, freewheeling diodes across inductive loads, e.g. relay coils, solenoid valves, prevent voltage spikes when the load is de-energized, protecting both the switching device and reducing conducted emissions into the control circuit. These suppression methods not only protect sensitive equipment, but also extend the life of switching components by reducing electrical stress. 4.2.3.4 Grounding and bonding. A robust, low-impedance earthing system is fundamental to EMC and overall machine safety. According to EN 60204-1, all exposed conductive parts of machinery and panels must be bonded to the protective earth PE to eliminate dangerous voltages and prevent static discharge. The earth bar inside the control panel should serve as a central bonding point for all shields, device earths, and protective earths. All equipment with metal enclosures, including sensors and drives, must have a dedicated earth connection using proper terminals and lugs, not relying on mounting screws for earthing. To maintain low impedance, earth connections should be as short and direct as possible, using appropriate conductor sizes, e.g. minimum 4 square millimeters for protective bonding in many cases, though this may vary depending on fault current levels. For panels containing sensitive electronic devices, such as PLCs and industrial PCs, an additional functional earth FE rail may be specified, connected directly to the main earth bar, but kept separate from the dirty earth of high-power equipment. 4.2.3.5 Routing and gland arrangements. Correct routing of cables in and out of control panels is essential to prevent EMI from entering or leaving the enclosure. All cable entries should use metal EMC glands, e.g. brass, nickel-plated, with 360-degree shield contact when shielded cables are used. This ensures that the shield is bonded to the panel's earth system right at the entry point, preventing the cable from acting as an antenna. Cables should be routed to avoid parallel runs of dissimilar circuits, e.g., avoid running 24-volt control lines alongside VFD output cables. Where external cable trays are used, ensure they are properly bonded to the main earth system, creating a continuous shielding structure. Control panel layouts should define clear separation zones, typically with vertical wire ducts for power and separate ducts for control signal wiring, with at least 50 mm physical separation, though this may vary depending on the voltages and currents involved. 4.2.3.6 EMC Summary. Addressing EMC during the design phase is essential for any control system to ensure reliable, fault-free operation. By applying correct cable shielding, effective earthing, proper routing and segregation, and appropriate filtering and suppression, controls engineers can prevent many of the intermittent and difficult to diagnose faults that plague poorly designed systems. Compliance with the EMC Directive 2014/30/EU, along with design principles outlined in EN 60204-1, not only ensures that machines are legally compliant, but also guarantees that they operate reliably in the often harsh and noisy environments of modern industrial facilities. 4.2.4 Electrical Design Summary. Although the physical assembly, wiring, and installation of control panels and field devices are usually handled by qualified electricians and panel builders, it is the controls engineer's responsibility to ensure that the system is designed correctly and safely from the outset. Electrical designs must be fully compliant with UK and EU standards, particularly EN 60204-1, IEC 61439, and BS 7671, and should also consider IEC 60947 for switchgear and control gear. Being aware of NFPA 79 for projects destined for North America is also beneficial. By focusing on correct component selection, safe circuit protection, structured panel layouts, and EMC practices, controls engineers ensure that systems are not only functionally robust, but also safe, maintainable, and compliant with all regulatory requirements. In summary, a properly designed control system reduces commissioning time, prevents operational issues, and protects both people and equipment, making careful electrical design a cornerstone of professional control engineering practice. 4.3 Troubleshooting and Support. 4.3.1 Systematic Troubleshooting and Fault Resolution for Controls Engineers. Controls engineers play a critical role in maintaining machine and process uptime, particularly in complex automated systems where electrical, mechanical, software, and network components are tightly integrated. Faults in such environments are often multifactorial, and resolving them requires a structured, methodical approach, supported by deep technical knowledge and advanced diagnostic techniques. A controls engineer's approach to troubleshooting must combine real-time diagnostic tools, in-depth system knowledge, and analytical methods to resolve issues efficiently and prevent recurrence. 4.3.2 Fault Diagnosis. Effective fault diagnosis begins with a disciplined method to narrow down and isolate the fault within electrical, mechanical, or software domains. Controls engineers must leverage a combination of diagnostic instruments and PLC system data to identify abnormal conditions. Key tools and methodologies include oscilloscopes, essential for capturing transient signals, analyzing communication waveforms, e.g. RS485, CN, Modbus RTU, detecting electrical noise, and validating sensor outputs. Useful for examining high-speed digital signals and PWM control lines. Multimeters and clamp meters for basic measurements such as voltage, current, resistance, and continuity. Crucial for verifying power supplies, control circuit integrity, and confirming proper earthing and bonding of components. Data loggers and PLC trace functions used to capture time sequence process variables and system states for identifying intermittent or sequence-dependent faults. High-resolution trend data is often key in diagnosing faults that only occur under specific conditions, e.g. high-temperature specific load. Industrial network analyzers, tools such as Profinet, Profibus analyzers, Ethernet, IP sniffers, and Wireshark for OPC UA or MQTT traffic to detect communication errors, retries, and signal degradation on industrial networks. Critical when troubleshooting distributed I/O, smart devices, and safety communication protocols, e.g. ProfiSafe, CIP safety. PLC and HMI diagnostics, leveraging built-in diagnostic functions within PLCs, e.g. Siemens S7 diagnostic buffer, Rockwell status bits, as well as user-defined fault flags and watchdog timers to pinpoint failures in I/O modules, network links, and software logic. Fault diagnosis should follow a systematic top-down or bottom-up approach, starting from general system symptoms, e.g., production halt, alarms, and progressively isolating individual components or subsystems based on gathered evidence. 4.3.3 Root Cause Analysis, RCA. Once the immediate fault is identified and isolated, controls engineers must focus on determining the true root cause rather than addressing only the superficial symptoms. RCA is essential to prevent recurring faults that could compromise safety, product quality, or productivity. Several analytical techniques are used in industrial automation for RCA. 5 whys. Analysis, asking why. Repeatedly, typically 5 times, to drill down beyond the surface issue to the fundamental cause. For instance, a motor trip may reveal issues in upstream control logic, environmental overheating, or incorrect load settings. Fault tree analysis, FTA. Constructing a logical diagram that maps out all possible causes of a fault condition using a structured tree format with and/or gates, which allows analysis of complex multipath failures, e.g., valve failed to open, could involve electrical, pneumatic, or command signal failures. Failure mode and effects analysis, FMEA. Systematically identifying all potential failure modes of a system and analyzing their impact, probability, and severity to prioritize corrective measures. Especially useful in safety-critical systems governed by ISO 13849 and IEC 62061, where understanding failure probabilities is necessary for achieving the correct performance level or SIL rating. Controls engineers must document RCA findings thoroughly, ensuring that maintenance teams, engineering managers, and system designers can review and learn from each incident. 4.3.4 Corrective actions and long-term solutions. Resolving a fault does not end at fixing the immediate issue. Controls engineers must implement both immediate corrective actions to restore operation and long-term improvements to prevent recurrence and enhance system reliability. Key aspects of corrective action include immediate repairs, replacing failed components, e.g., sensors, relays, drives, re-terminating faulty wiring and restoring correct connections, software corrections for identified logic faults or improper sequencing, design adjustments, rewriting control logic to include enhanced error detection and fail-safes, e.g., adding timeouts, interlock checks, or diagnostics. Hardware upgrades such as replacing underrated contactors, specifying industrial-grade sensors for harsh environments, or improving enclosure cooling if temperature was a contributing factor. Improved EMC design if faults were related to electrical noise, e.g., rerouting cables, adding filters, or enhancing earthing schemes. 4.3.5 Maintenance and procedural updates, updating preventive maintenance, PM schedules to include checks for failure-prone components, e.g. motor mega testing connector inspections, training operators and maintenance technicians on newly identified risks, and providing updated fault response procedures. Ensuring spare parts availability for critical components identified as potential single points of failure. Where faults have a functional safety impact, controls engineers must reassess the system's safety function performance, verifying that performance level, PL or SIL targets remain valid following the fault and corrective actions. 4.3.6 Closing the feedback loop for continuous improvement. Beyond technical repairs, controls engineers should contribute to continuous improvement by feeding RCA results into system design reviews, supporting future upgrades, and improving overall plant resilience. Lessons learned from fault investigations should inform design of new systems, incorporating lessons into new panel builds and software, standardization of components and software modules to avoid repetition of previously identified weaknesses, company-wide training and knowledge sharing to ensure broader engineering teams benefit from individual fault investigations. 4.3.7 Troubleshooting Summary. Systematic troubleshooting and fault resolution are core responsibilities for controls engineers. They require analytical thinking, advanced diagnostic techniques, and deep system knowledge. Through structured fault diagnosis, rigorous root cause analysis, and comprehensive corrective actions, controls engineers ensure maximum uptime, system reliability, and safety. Their role extends beyond simply fixing issues to preventing future failures, through continuous improvement of design, processes, and maintenance practices. 4.4 Commissioning and Startup. 4.4.1 Commissioning, Safety, and Continuous Improvement in Control System Design. The commissioning phase is where control system designs are transformed from theoretical concepts and drawings into fully operational functional systems. This phase is a critical milestone, and the responsibility for successful delivery rests heavily on the controls engineer. It is during commissioning that the final validation of PLC, safety systems, HMIs, SCADA, and network integration takes place, confirming that everything operates as intended, safely, reliably, and in line with regulatory standards. 4.4.2 System Validation. Controls engineers are responsible for rigorous functional testing of the system to ensure that all components work as designed and that the control logic matches the required process sequences. Key aspects of system validation include testing, PLC logic, and sequences under real-world conditions, ensuring all set points, interlocks, and transitions perform correctly. Validating safety circuits, including emergency stops, interlocks, light curtains, and safety PLC logic, confirming that all safety functions meet performance level or SIL targets derived from the original risk assessment. Verifying HMIs and SCADA interfaces, ensuring that process variables, alarms, and diagnostics are correctly displayed and that operator controls function as expected. Confirming fail-safe and fault handling routines, ensuring that faults trigger appropriate system responses and do not create unsafe conditions. All validation activities should be thoroughly documented and reviewed against design specifications and safety requirements. 4.4.3 Integration Testing. Beyond individual system elements, controls engineers are responsible for end-to-end system integration testing, where the interaction of all hardware and software elements is confirmed in a live environment. This includes testing mechanical and electrical integration of field devices, valves, motors, sensors, with PLC control logic, and ensuring feedback signals are reliable and accurate. Coordinating motion systems such as servo drives and multi-axis robots, ensuring precise synchronization and safe operation under all operating conditions. Validating communication networks including industrial Ethernet, Profinet, Ethernet IP, field bus systems, and safety networks, e.g. ProfiSafe, DIP safety, confirming data integrity and fault tolerance, ensuring that inter-machine and system-level communications are working, e.g. between packaging lines, conveyors, and palletizing robots. This testing ensures that the entire system functions as a cohesive unit, with all components communicating and interacting properly. 4.4.4 Operator Training. No system is complete without ensuring that operators and maintenance personnel understand how to safely and effectively operate it. Controls engineers are responsible for delivering structured, comprehensive training, covering system operation, how to start, stop, and adjust the system during normal and abnormal conditions. HMI and SCADA use navigating screens, responding to alarms, and using diagnostic tools provided in the interface. Basic fault finding and reset procedures, enabling operators to respond to common issues without needing engineering intervention. Safety systems and emergency procedures, including what happens when a safety device is triggered and how to recover safely. Training should be documented and ideally accompanied by operator guides and quick reference manuals. 4.4.5 Documentation. Controls engineers are responsible for generating complete and accurate commissioning documentation, critical for both system handover and future maintenance. Key deliverables include functional acceptance testing, FAT, and site acceptance testing, SAT reports, detailing what was tested, how it was tested, and the results. As built electrical schematics and wiring diagrams, updated to reflect any changes made during commissioning. User and maintenance manuals covering system operation, maintenance intervals, and troubleshooting guidelines. Safety documentation, including safety circuit validation records, PL/SIL verification, and compliance certificates. Well-prepared documentation is vital for ongoing support, legal compliance, and effective future upgrades. 4.4.6 Safety and Compliance. 4.4.6.1 Functional Safety Design. Controls engineers must design and validate functional safety systems to ensure that machinery meets relevant safety integrity levels. This includes safety-rated PLCs, relays, and devices selected to achieve required performance levels, PL, under ISO 13849, or safety integrity levels, SIL, under IEC 62061, depending on the risk assessment outcomes. Validation of safety functions, such as emergency stops, guard interlocks, and safe motion, STO, SS1, ensuring they perform correctly under fault conditions. Fault exclusion and common cause failure analysis, ensuring that safety systems meet both the reliability and independence requirements necessary for compliance. Detailed safety validation ensures that all identified risks are mitigated and that legal and regulatory obligations under Machinery Directive 2006/42/EC and UK Supply of Machinery Safety Regulations 2008 are met. 4.4.7 Regulatory adherence. Controls engineers must ensure designs comply with applicable UK, EU, and international standards, including Machinery Directive 2006/42/EC and its UK equivalent, governing overall machinery safety, EN 60204-1 for electrical safety in machine systems, IEC 61439 for panel construction, NFPA 79, where US compliance is required for exported machinery, IEC 62443 for industrial cybersecurity, ensuring safe remote access and secure communication. Compliance includes documentation, CE/UKCA marking, and declaration of conformity, often requiring collaboration with notified bodies or third-party assessors for complex or high-risk machinery. 4.4.8 Continuous improvement. 4.4.8.1 Optimization projects. Controls engineers play a key role in ongoing system optimization, using operational data to identify inefficiencies and areas for enhancement. Control logic tuning, including PID optimization and sequence adjustments, to improve performance and cycle times. Component upgrades such as replacing aging drives or motors with higher efficiency alternatives. Bottleneck analysis, using production data to pinpoint slow points in the process and develop technical solutions, e.g., resequencing tasks, load sharing. 4.4.8.2 Predictive maintenance. Modern systems benefit from condition monitoring and predictive maintenance, and controls engineers must integrate these capabilities into the system. Sensor-based monitoring, e.g., vibration, temperature, current, to track machine health. Data analytics platforms linked to PLC SCADA systems for real-time diagnostics. Machine learning algorithms to detect deviations from normal operation and predict failures before they occur, enabling proactive maintenance scheduling. 4.4.8.3 Technology evaluation. Controls engineers are responsible for evaluating new technologies and automation trends to keep systems competitive. Artificial intelligence-driven process control for smarter adaptive systems. Digital twins for virtual commissioning and real-time simulation. Wireless sensor networks, and IIoT for flexible, scalable data acquisition. Edge computing and decentralized control architectures, reducing latency and improving resilience. By reviewing and piloting emerging solutions, controls engineers ensure that systems remain efficient, secure, and future-proof, supporting long-term operational goals. 4.4.9 Commissioning summary. From commissioning to continuous improvement, controls engineers drive the full life cycle of industrial automation systems. Their role spans system validation, safety compliance, optimization, and technology integration, ensuring that systems are delivered safely, operate reliably, and evolve over time. Through detailed testing, documentation, and technical leadership, controls engineers ensure the success of modern industrial operations. 4.5 The evolving role of controls engineers. As industrial automation continues towards Industry 4.0 and beyond, the role of the controls engineer is expanding rapidly. Engineers must stay abreast of technological advancements such as artificial intelligence, advanced robotics, cybersecurity, and digitalization strategies to ensure automation systems remain resilient, efficient, and competitive in a rapidly evolving industry landscape. In essence, controls engineers are the architects of industrial automation, essential for translating theoretical automation concepts into practical, functional, and robust production systems. Their role is central to industrial progress, bridging disciplines, driving innovation, and ensuring safe, reliable, and efficient production systems. 5 key components of automation systems. An industrial automation system is a collection of interconnected components that perform precise control over machinery and processes. Designing such systems requires a deep understanding of both the individual components and how they interact within a larger control architecture. The following sections outline the fundamental building blocks of modern automation systems. 5.01 PLCs, HMIs, and SCADA. Programmable logic controllers, PLCs, are deterministic, real-time industrial controllers used to execute sequential and process logic. PLCs are selected based on processing speed, I/O count, safety functions, motion control capabilities, and communication protocols. Key considerations: compliance with IEC 61131-3 for standardized programming languages, ladder, structured text, FBD, SFC. Safety-rated PLCs compliant with ISO 13849-1, IEC 62061, and IEC 61508 for functional safety applications PLESIL3. Integrated motion and safety for machines requiring coordinated drives and safety functions, e.g., using safety-rated Profinet and ProfiSafe or EtherCAT FSOE. Support for industrial protocols: Ethernet/IP, Profinet, EtherCAT, Modbus TCP, OPC UA. Human-machine interfaces, HMIs, provide operational insight and control over industrial processes. When designing HMIs, follow ISA 101 for high-performance HM. I designed to minimize operator error and alarm fatigue. Includes safety-critical information, e.g., active emergency stops, safety circuit status, in clear, prioritized visual formats. Ensure secure communication with PLCs using TLS encrypted protocols where supported, e.g., OPC UA Secure, MQTT with TLS. SCADA, supervisory control and data acquisition, systems provide centralized monitoring and control over distributed plant equipment, used for real-time data acquisition, alarm management, and historical data logging. Integration with MES, manufacturing execution systems, and ERP for production tracking and OEE calculations. SCADA systems should comply with ISA 95 hierarchy models for enterprise integration. 5.0.2 Sensors and actuators. Sensors form the input layer of an automation system, providing critical feedback used by PLCs to execute logic. Selection criteria must consider response time, resolution, signal type, analog, digital, and safety rating if part of a safety function. Position and presence detection, inductive capacitive proximity sensors, EN 60947-5-2, photoelectric sensors, EN 60947-5-2, linear and rotary feedback, encoders and resolvers, often used in SELPL motion safety loops. Process variables, analog sensors, e.g., 4 to 20 milliamps, 0 to 10 volts. For pressure, EN 837, flow, temperature, and force. Safety sensors, light curtains, laser scanners, interlocks, and pressure mats, certified to ISO 13849-2, IEC 61496. Actuators are output devices that physically perform actions based on control signals. Actuator design must consider fail-safe positioning, reaction time, and safety category when involved in emergency or safety systems. Motors, AC, DC, servo, and stepper motors, selected based on torque speed requirements and dynamic response. Valves, pneumatic and hydraulic valves, ISO 5599-1, ISO 1219, including monitored safety valves. Relays contactors, for high current loads, must comply with IEC 60947-4 and be used appropriately in safety circuits, e.g., force-guided relays. Solenoids, direct on-off control of mechanical systems, including lock-unlock functions in safety systems. 5.0.2.1 Motors, drives, and motion control. Motors and drives are central to moving parts of a machine. Their selection and control architecture are critical to ensuring precise, safe, and reliable operation. AC induction motors, IEC 6034, general purpose motion and pumps, servo motors, EN 61800-5-2 compliant drives, high precision, closed loop control, typically used in robotics, packaging, CNC, stepper motors, low cost positioning, but typically open loop unless equipped with encoders.
Drive selection and design considerations.
Variable frequency drives, VFDs for speed control of AC motors, IEC 61800-2, servo drives with integrated safety functions, STO SS1, SLS SSR as per IEC 61800-5-2. Networked drive systems using protocols like EtherCAT with FSOE, Profinet ProfiSafe, or Ethernet IP CIP safety for distributed motion. Feedback devices, encoders, resolvers for closed loop control. Key motion safety considerations. Safe torque off, STO, for immediate motor deactivation, compliant with SIL 3PLE. Safe stop 1, SS1, for controlled stopping before disabling torque. Safe limited speed, SLS, safe direction, SDI, and other advanced safety functions for hazardous motion zones. 5.0.3 Pneumatics and Hydraulics Basics. Pneumatics and hydraulics provide mechanical motion using compressed air or pressurized fluids. While basic, their safety integration and control design are critical to system performance and compliance. Pneumatics design principles.
Actuators, cylinders, grippers, and rotary actuators sized for force and stroke.
Valves, directional control valves, ISO 5599-1, proportional valves for variable control, safety-rated dump valves, air preparation, filter regulator lubricator, FRL units for system protection. Safety integration, use of monitored pneumatic safety valves compliant with ISO 13849-1, Category 3 or 4 for energy isolation in emergency stops.
Hydraulics design principles.
Actuators, cylinders, and motors for high force applications. Valves, directional and pressure control valves designed to handle fluid under extreme pressure, ISO 1219, ISO 4413. Safety requirements. Hydraulic safety functions for load holding, safe lowering, and pressure release in compliance with ISO 13849 and EN 602041 energy isolation clauses. Pressure monitoring using certified sensors, PL- and higher where required. Fail-safe design, use of counterbalance valves and monitored blocking valves to prevent unintended movement under loss of pressure or power. Important note, both pneumatic and hydraulic systems must be designed with energy isolation and safe release of stored energy in fault conditions, in line with EN 60204-1, ISO 4413, and ISO 4414. 6. Common factory machines and systems. Industrial automation encompasses a wide range of machines and systems that perform material handling, part manipulation, machining, and assembly. The efficiency and reliability of a factory largely depend on how well these machines are integrated, controlled, and maintained. This section covers some of the most common types of factory automation equipment, focusing on their design considerations, control system integration, and safety requirements. 6.0.4 Common factory systems. Common factory machines and systems include a wide range of equipment typically controlled by PLCs. Conveyors and material handling systems form the backbone of most production lines, where the PLC manages motor control, tracking sensors, diverters, and synchronization with upstream and downstream equipment to ensure smooth product flow and accumulation. Robotic systems, including 2, 3, 4, and 6-axis robots, are widely used for tasks such as pick and place, welding, packaging, and palletizing. The PLC coordinates robot operation, synchronizes conveyors or indexing tables, and manages interaction with safety devices like light curtains and interlocked guards. Automated palletizing and packaging systems rely on the PLC to handle motion control for robots and gantries, manage in-feed conveyors, adjust for different product types, and ensure proper stacking and wrapping of pallets ready for dispatch. Pick and place and assembly systems are used to move, position, and assemble parts using a combination of servo motors, pneumatic actuators, and sensors. The PLC coordinates all movements, timing, and sequencing to ensure accurate placement and efficient operation, often including safety interlocks and process verification. Filling, capping, and bottling lines are controlled by PLCs to manage dosing, product flow, valve actuation, and conveyor speeds. The PLC ensures that each container is filled to specification, capped or sealed properly, and transported downstream without spillage or damage. Inspection and vision systems use the PLC to process pass, chock, fail signals from cameras or sensors, control reject mechanisms, and log inspection data. These systems are critical for quality control, verifying dimensions, labels, and surface defects in real time as products move along the line. Extrusion and forming machines used in plastic, metal, and composite industries depend on PLCs to control temperatures, pressure, motor speeds, and safety interlocks. The PLC ensures material is formed to exact specifications while maintaining process stability and safety compliance. Heavy metal forging and press systems are typically controlled by PLCs that sequence hydraulic or mechanical presses, manage die movements, regulate force application, and control guarding and interlocks to ensure operator safety and proper forming of high-strength components. Coating, painting, and finishing lines rely on the PLC to coordinate conveyors, robotic arms, spray heads, and curing ovens. The PLC adjusts paint flow rates, robot positioning, and bake times, ensuring consistent surface coverage and quality. Welding and joining stations are controlled by PLCs to manage welding sequences, control clamping mechanisms, synchronize multi-axis movements, and monitor safety devices. These stations ensure precise weld quality and repeatable joining processes. Powder and bulk material handling systems, such as those in the food, chemical, and pharmaceutical industries, use PLCs to control conveyors, dosing equipment, weigh scales, and level sensors. The PLC manages recipe control, batching, and flow regulation to ensure accurate handling and mixing. Heat treatment and furnace systems are governed by PLCs that regulate temperature profiles, control gas flows, manage timing, and ensure safety interlocks are in place for processes like hardening, annealing, and tempering. Sorting systems and automated storage and retrieval systems, ASRS, are driven by PLCs that direct conveyor diverters, lifts, and shuttles to manage product sorting, storage, and retrieval efficiently. The PLC interfaces with higher level systems for inventory tracking and order fulfillment. These systems represent the core of factory automation, with the PLC at the center of motion control, process logic, safety coordination, and system communication. 6.05. What a controls engineer should learn from common systems. Understanding how typical factory systems operate teaches controls engineers how to design automation solutions that are both practical and robust. One of the most important lessons is the need to integrate multiple technologies combining PLCs with drives, sensors, safety devices, robotics, and vision systems. An engineer must be able to tie these elements together in a way that is reliable, flexible, and responsive to production demands.
Another critical area is the role of functional safety. Every industrial machine, whether a simple conveyor or a complex palletizer, must be designed with appropriate safety measures, including emergency stops, interlocks, light curtains, and safe torque-off (STO) for motion systems. Engineers need to understand how to apply standards such as ISO 13849 and IEC 62061, ensuring that the safety design matches the machine's risks and operational requirements.
Modern control systems also require clear built-in diagnostics and fault handling. Systems must detect, report, and respond to faults automatically, so operators and maintenance teams can react quickly. Whether it's a failed sensor, an overload, or a communication fault, the system should provide clear alarms and help guide troubleshooting to reduce downtime. A key part of modern automation is data handling and connectivity. Factory machines are now expected to provide real-time data to higher-level systems like MES, ERP, or SCADA. This requires engineers to understand industrial communication protocols such as Profinet, Ethernet IP, OPC UA, and MQTT, and how to make PLC data available for production tracking, quality control, and predictive maintenance. Finally, all complex systems must be designed to be modular and maintainable. Using structured programming, IEC 61131-3, reusable code blocks, and scalable hardware designs, ensures that systems can be adapted over time, whether for new products, process changes, or technology upgrades. Well-structured designs also make troubleshooting easier for future engineers and technicians who will maintain the system in the long term. 7. Electrical, safety, and regulatory standards. 7.1 Industrial electrical design. 7.1.1 Control panel design and layout. Control panel design is critical to the safe, reliable, and efficient operation of automation and industrial control systems. In the UK and EU, control panel designs must comply fully with EN 60204-1, Safety of Machinery, Electrical Equipment of Machines, ensuring both operational integrity and regulatory compliance. While NFPA 79 applies similarly in the US, engineers designing systems for UK or European applications must prioritize EN 60204-1 and associated UK-EU regulations. A properly designed control panel not only meets regulatory compliance, but also significantly improves maintainability, reliability, operational safety, and overall system lifecycle efficiency. The following sections detail key technical considerations for UK controls engineers during the design phase. 7.1.2 Panel layout and ergonomics. The physical arrangement of components within a control panel should be logical, intuitive, and structured for easy maintenance and troubleshooting. Major guidelines include the control panel should be arranged with a logical flow, typically starting with power entry components, main isolator and circuit protection, at the top or left side, followed by power distribution devices, contactors, relays, controllers, PLCs, I/O modules, and terminating clearly at signal level components or terminals. All items must be clearly identified in drawings and on the panel itself, per EN 60204-1 and IEC 81346. Engineers must provide adequate clearances around components, both for cooling and ease of maintenance. Referencing the specific manufacturer's installation manuals for each device is essential, as they often prescribe minimum clearances around drives, PLC modules, power supplies, transformers, and contactors for proper heat dissipation. Heat-sensitive devices, such as variable frequency drives, VFDs, servo amplifiers and transformers, often have strict spacing requirements to maintain reliable operation. Cable routing and management within the panel must follow clear paths to avoid crosstalk, reduce electromagnetic interference, EMI, and simplify maintenance access. Good practice is to use dedicated trunking for signal cables and separate trunking for power cables. Clear documentation showing cable segregation and routing must be included in design packs. Power circuits, 230/400 volts AC, must be clearly separated from low voltage control and signal circuits, 24 volts DC, to minimize EMI and to comply with EN 60204-1 recommendations. A physical gap, separate cable trays, or different wire ducts should be designed into the panel layout to ensure compliance. 7.1.3 Component selection and placement. All components used in the panel must be carefully selected, rated, and placed appropriately according to their electrical load, environmental conditions, and frequency of use. Key technical considerations include selection of components such as contactors, circuit breakers, MCBS, MCCBS, relays, power supplies, and terminal blocks must align with calculated load currents, short circuit levels, and expected operating conditions. Compliance with standards like IEC 60947 series for switchgear and IEC 60269 for fuse protection is mandatory. When placing heat-generating components such as power supplies, transformers, and VFDs, controls engineers must ensure sufficient free space around the components as specified in each component's installation manual. Manufacturers often provide minimum clearances for effective heat dissipation, typically at least 50 to 100 mm clearance on all sides. Where thermal management is critical, thermal analysis or calculations may be required during design to confirm ventilation and cooling requirements. Components that require frequent maintenance access, such as PLCs, relays, fuse holders, and circuit breakers, should be placed in accessible locations within the panel. Clear access and unobstructed visibility improve troubleshooting efficiency and minimize downtime. Safety critical items such as emergency stop relays or safety PLC modules should also be easily accessible and clearly identifiable. 7.1.4 Enclosure Considerations. Selecting and designing control panel enclosures correctly is crucial for ensuring environmental protection, thermal management, and safety compliance. Enclosures must meet appropriate ingress protection IP ratings as per IEC 60529, suitable for their installed environment. For standard indoor industrial applications in the UK, IP54 enclosures are commonly used, protecting internal components against dust and water spray. For harsher environments, e.g. outdoors or washdown areas, higher IP ratings such as IP65 or IP66 may be required. Enclosure ratings should be clearly specified in the design documentation.
Effective thermal management is vital, particularly for panels containing electronics sensitive to heat. Controls engineers must assess whether natural ventilation is sufficient or if active cooling solutions, fans, heat exchangers, air conditioners, are required. Panels containing drives, transformers, or high current devices typically require active cooling. Thermal calculations, using heat dissipation values found in component manuals, help determine cooling capacity requirements.
Proper earthing, grounding, and bonding of enclosures is mandated by EN 60204-1. All metal parts of the enclosure must be effectively bonded to the protective earth PE system, typically through dedicated earth studs or bars. Functional earthing FE for sensitive electronics may be necessary, ensuring low impedance grounding paths. Engineers must ensure compliance with the standard by including clearly documented earthing schemes in the control panel design.
7.1.5 Compliance with UK and EU regulations.
Control panels in the UK must fully comply with UK Supply of Machinery Safety Regulations 2008 based on the EU Machinery Directive 2006/42/EC. These regulations mandate comprehensive technical documentation, including detailed electrical schematics, panel layouts, bills of materials, risk assessments, and functional safety validations. All panels must be appropriately CE or UKCA marked, with supporting technical files readily available for verification. For engineers designing machinery for the US market, familiarity with NFPA 79 is necessary. While similar in scope to EN 60204-1, NFPA 79 differs in specific requirements regarding conductor sizing, wire coloring, and component specifications, often referencing UL-listed components. Control panel design is not simply about placing components in an enclosure. It requires detailed attention to layout ergonomics, component specifications, clearances, environmental protection, thermal management, and rigorous compliance with relevant standards. Controls engineers in the UK must diligently follow the requirements outlined in EN 60204-1 and associated IEC standards, carefully reference manufacturer documentation, and ensure that all design choices enhance safety, reliability, maintainability, and regulatory compliance. 7.2 Safety and Regulatory Standards. 7.2.1 Machine Safety Systems. Overview. Machine safety systems are essential elements of industrial automation designed to reliably protect operators, maintenance personnel, and machinery itself from potential hazards during both normal operation and emergency conditions. In the UK and EU, safety systems for machinery must comply with strict regulatory standards defined primarily by the Machinery Directive 2006/42/EC and the corresponding UK Supply of Machinery Safety Regulations 2008. Adherence to these regulations and standards ensures safety compliance and minimizes risk.
Below are essential safety components and systems with detailed technical considerations for compliance and effective implementation. 7.2.2 Emergency Stop Systems (ESTOPs).
Emergency stop systems are vital safety components intended to quickly halt machinery and processes in hazardous situations. According to ENISO 13850, emergency stops must be clearly identified, typically red mushroom-headed buttons on a contrasting yellow background. Be installed in readily accessible locations for immediate operation without obstruction. Require manual reset after activation, ensuring machinery does not automatically restart. Reliably remove or isolate power from actuators and hazardous moving parts through safety-rated switching devices. Operate using positive opening contact mechanisms to prevent failure under fault conditions. Emergency stops must not serve as functional stopping devices. They must be tested regularly, and the control system must continuously monitor the integrity of emergency stop circuits, typically using dual-channel monitoring for redundancy and detection of faults. 7.2.3 Safety Relays and Safety Controllers. Safety relays and safety controllers are specialized, safety-rated devices designed specifically to perform and supervise safety functions. Compliance with ISO 13849-1, Performance Level PL, and IEC 62061, Safety Integrity Level SIL. Standards is mandatory depending on the risk assessment and required safety level for the application. Safety relays and controllers must provide fail-safe monitoring and control of safety functions such as emergency stops, interlocks, and light curtains. Detect single faults through redundancy and diagnostic functions, ensuring dangerous conditions cannot arise unnoticed. Be chosen according to the determined PL, PLA to PLE, or SIL, SIL1 to SIL3, based on the required safety integrity derived from machine risk assessments. Ensure rapid response times, clearly documented by manufacturers and verified during commissioning and testing phases. Provide outputs that utilize positively guided relay contacts or solid-state safety outputs, OSSDs, to reliably remove power from hazardous machine components. Safety controllers, safety PLCs, are increasingly popular for complex safety applications, allowing sophisticated safety logic, diagnostics, communication of safety states via safety field buses, such as ProfISafe or CIP safety, and integration with standard control systems, providing greater flexibility and visibility. 7.2.4 Safety Interlocks and Light Curtains. Safety interlocks and light curtains, electrosensitive protective equipment, ESPE, are widely used for safeguarding hazardous machinery areas, restricting or detecting unauthorized or unsafe access. Compliance with EN/ISO 14119, interlocking devices, and IEC 61496 ESPE is required. Safety interlocks must be mechanically and electrically robust, securely preventing the opening of doors or covers during hazardous operations. Feature positively opening contacts or electronically monitored contacts to detect and react to any tampering or device failures. Provide clear diagnostics and status indication to alert operators of interlock status or potential faults. Offer options such as guard locking, power to lock or power to release, depending on machine hazard conditions. Light curtains must conform to IEC 61496, classified as Type 2 PLC/SIL1 or Type 4 PLE/SIL3, depending on the assessed risks of the machinery. Be correctly positioned, preventing operators from inadvertently bypassing detection zones. Provide clearly defined detection zones and response times specified by the manufacturer, which must be considered during installation and commissioning. Be integrated directly into safety circuits monitored by safety relays or controllers, achieving the required safety performance levels. 7.2.5 UK and EU regulatory compliance. In the UK and Europe, machinery safety systems must meet the requirements of the Machinery Directive 2006/42/EC and the UK Supply of Machinery Safety Regulations 2008. This includes performing comprehensive risk assessments, documenting safety designs, and clearly demonstrating compliance through technical files, CE or UKCA marking, and conformity declarations. Engineers must follow detailed standards, EN/ISO 13849, IEC 62061, IEC 60204-1, IEC 61496, EN/ISO 14119, and others to achieve compliance. When designing machinery for export to the US market, compliance with NFPA 79 and OSHA guidelines is also necessary. Although similar in intent, NFPA 79 often references UL-approved safety components, slightly differing wiring and design practices. 7.2.6 Safety Standards. Summary: machine safety systems are not merely about achieving compliance, they are about reliably ensuring safety in all foreseeable conditions. Controls engineers must select, design, and integrate these systems according to detailed UK-EU regulations, meeting the stringent safety performance levels defined by PL and SIL standards. Careful selection of emergency stops, safety relays, controllers, interlocks, and light curtains, coupled with robust safety validation and documentation, ensures machinery can operate safely and efficiently throughout its life cycle. 7.3 Functional Safety, SIL, PL categories. Functional safety is the approach taken to ensure machinery operates safely, even if something goes wrong. It involves designing systems that reliably detect faults or dangerous conditions, safely shut down or control equipment to avoid injury, and protect machinery from damage. To achieve this, standards like SIL safety integrity level and PL performance level define clear safety requirements. It's important to note that although SIL and PL provide complementary measures, they should not be mixed within the same safety function or system design. Engineers should choose one standard, either SIL IEC 62061 or PL ISO 13849, and apply it consistently throughout each safety function.
7.3.1 Technical explanation, functional safety, SIL, performance levels, and safety categories.
Functional safety refers specifically to aspects of machinery safety that depend on the correct functioning of electrical, electronic, or programmable systems. Its goal is to guarantee safe and predictable system responses to faults or hazardous conditions. Safety requirements for machinery in the UK and EU are primarily governed by ISO 13849-1, PL and category, and IEC 62061, SIL. Controls engineers must clearly select one of these standards per safety function. Combining PL and SIL ratings within the same safety function is not advised due to differences in evaluation methods and terminology, which can lead to confusion and difficulty in validation. 7.3.1.1 Safety Integrity Level. The Safety Integrity Level, SIL, defined in IEC 62061 and IEC 61508, classifies the safety integrity requirements of control systems into levels from SIL1, lowest risk applications, to SIL4, highest integrity required, used in critical sectors like nuclear or aerospace. Industrial machinery typically employs SIL ratings of 1 to 3. Achieving a certain SIL involves selecting safety-rated components, employing redundancy, fault diagnostics, and fault tolerance, and validating safety functions through structured methods outlined in IEC 62061. 7.3.1.2 Performance Levels PL. Similarly, performance levels PL, introduced by ISO 13849-1, define safety performance requirements based on the severity of potential injuries, frequency of exposure, and possibility of hazard avoidance. Performance levels range from PLA lowest to PLE highest. Engineers select appropriate safety components, architectures, and validation methods to achieve these required performance levels, typically applied to discrete safety functions such as emergency stops, safety interlocks, and safety sensor circuits. 7.3.1.3 Safety Categories, CAT. Safety categories, CAT, also defined by ISO 13849-1, describe specific hardware architectures that support achieving the targeted PL. Categories B, 1, 2, 3, and 4 range from basic to highly redundant and fault-tolerant architectures. Higher categories, such as CAT3 or CAT4, utilize redundant components, advanced diagnostics, and continuous monitoring to ensure the system remains safe even in the event of component failure. Controls engineers should carefully choose between SIL and PL methodologies based on project requirements, machinery type, and regional standards, and they should avoid mixing the two within the same safety function or subsystem. Clear, detailed documentation of the selected safety standard and its implementation must be maintained to confirm compliance and support long-term operational safety and regulatory approval. 7.4 Key Safety Standards, ISO 13849, IEC 62061, NFPA 79. Safety standards guide engineers on how to design, build, and validate safety functions within industrial machinery control systems. Compliance ensures machines operate safely, reliably, and in accordance with legal requirements. In the UK and EU, the main standards relevant to controls engineers designing machinery safety systems are ISO 13849-1 and IEC 62061, while NFPA 79 is an important standard when exporting or working with machinery designed for the North American market. 7.4.1 ISO 13849-1, ISO 13849-1 Safety of Machinery, Safety-Related Parts of Control Systems, provides a structured approach to designing safety control systems by defining 5 performance levels, PLs, PLA through PLE. Each level reflects a different requirement of reliability and fault tolerance, with PLE representing the highest reliability and lowest probability of dangerous failures. ISO 13849-1 helps engineers determine the required performance level based on the severity of potential injury, frequency of exposure to the hazard, and likelihood of hazard avoidance. The standard provides guidance on selecting appropriate safety-rated components, designing robust safety circuits, including redundant architectures and diagnostic testing, and validating the achieved performance level through calculation and testing. 7.4.2 IEC 62061 IEC 62061 Functional Safety of Machinery specifies safety requirements using safety integrity levels, SIL. SIL ratings range from SIL 1, lowest level of safety integrity, to SIL 4, highest level, typically applied in critical applications beyond typical manufacturing scenarios, such as nuclear or rail transport. Industrial machinery commonly requires SIL 1, SIL 2, or SIL 3. IEC 62061 defines comprehensive guidelines on how to select and integrate safety-rated controllers, relays, sensors, and actuators into machinery control systems, alongside clear processes for validating safety functions. Engineers following IEC 62061 must carefully document their safety design process, including risk assessment methodologies, SIL determination, component selection criteria, fault exclusion reasoning, common cause failure analysis, and safety validation testing. 7.4.3 NFPA 79. NFPA 79, Electrical Standard for Industrial Machinery, is primarily relevant to machinery destined for installation or sale in North America. It defines the electrical requirements of industrial machines, focusing heavily on safety of wiring methods, cable sizing, grounding practices, protection devices, and machine-level emergency stop arrangements. Although similar in intent to EN 60204-1, NFPA 79 often specifies the use of UL-approved components, particular wire colors, and certain North American-specific installation practices that differ slightly from UK and EU norms. Controls engineers must understand these differences clearly when designing equipment destined for the US market to ensure compliance and regulatory approval. Cross-referencing standards and understanding the overlap between ISO 13849-1 and IEC 62061 allows engineers to ensure international compliance, enabling machinery to be sold and used safely across global markets. However, it's important to use either ISO 13849 performance levels or IEC 62061 safety integrity levels consistently for a given safety function without mixing the two to maintain clarity and compliance during safety validation processes. Applying these key standards diligently allows controls engineers to design systems that meet rigorous safety, regulatory, and customer-specific requirements, achieving full CE or UKCA marking, legal compliance, and global market acceptance. 7.5 Risk Assessments and Safety Circuit Design. Risk assessments form the foundation for machinery safety and must be conducted systematically and thoroughly. They should ideally be performed early in the design phase of any new machine or system, during modifications or upgrades of existing equipment, or following accidents or near-miss events. A comprehensive risk assessment not only ensures regulatory compliance, e.g., Machinery Directive 2006/42/EC, ISO 12100, but also directly contributes to creating a safe working environment. 7.5.1 Conducting an effective risk assessment. An effective risk assessment typically involves a cross-functional team, including controls engineers, mechanical engineers, operators, maintenance personnel, and safety professionals. Each member contributes different expertise, ensuring comprehensive hazard identification and realistic evaluation of risks. The risk assessment process involves several key stages, starting with clearly identifying hazards. This initial stage systematically considers all potential hazards associated with normal machine operation, maintenance, setup, cleaning procedures, and even reasonably foreseeable misuse scenarios. Typical hazards identified include mechanical risks such as crushing, entanglement, or pinch points, electrical hazards including shock or burns, thermal hazards like heat exposure, ergonomic concerns related to repetitive tasks or physical strain, and chemical hazards involving exposure to harmful substances.
Once identified, each hazard must then be evaluated based on two critical criteria: likelihood and severity. Likelihood describes how probable it is that the hazardous event will occur. Factors influencing this include the frequency of the task, duration of exposure, existing safety measures, operator reliability, and historical incident data. Likelihood is typically categorized as very unlikely, unlikely, possible, likely, or very likely. Severity defines the potential extent of harm or injury that might result if the hazardous event occurs. Severity categories range from negligible, involving minor discomfort with no significant injury, through minor, moderate, requiring first aid, significant, serious injury requiring medical intervention, to severe, potentially resulting in permanent disability or even fatality. Using a risk assessment matrix helps clearly visualize and prioritize risks based on the combination of these likelihood and severity factors.
For hazards evaluated as medium or high risk, the controls engineer must define the required safety integrity, either a performance level, PL according to ISO 13849-1, or a safety integrity level, SIL, as per IEC 62061. This explicitly defines the necessary reliability, fault tolerance, and robustness of the protective measures needed to mitigate the identified risks effectively. Following this determination, the engineer specifies detailed risk reduction measures clearly. These typically include safeguarding methods like physical guards, safety interlocks, and electrosensitive protective equipment, such as light curtains. Additional risk reduction may involve implementing emergency stops, safe control circuits, often dual-channel monitored systems, clear operational procedures, signage, specialized operator training, and the provision of appropriate personal protective equipment, PPE. The final stage involves thorough documentation and validation of the risk assessment process and outcomes. Clearly recording the identified hazards, evaluated risks, and implemented safety measures is essential. Validation must include verifying through functional tests, formal design reviews, and documented validation protocols that all safety measures effectively reduce risk to acceptable levels, ensuring ongoing safety and compliance. 7.5111
Tips for effective risk assessments.
Involve experienced operators and maintenance staff. They offer invaluable practical insights into potential hazards and realistic operating scenarios. Use checklists and structured approaches, e.g. ISO 12100 templates, to ensure no hazards are overlooked.
Clearly document assumptions, reasoning behind decisions, and justification for risk ratings.
Regularly review and update the assessment, particularly after incidents or machine modifications. Clearly define terminology, e.g. likelihood, severity, to ensure consistency and clarity. Keep the assessment concise, yet detailed enough to be clearly understood and practically applied by all stakeholders. 7.51.2 Structuring the risk assessment document. A clearly structured risk assessment document ensures clarity, ease of review, and compliance verification. Typically, the document begins with an introduction, clearly stating the purpose, scope, and description of the machinery or process being assessed, including details of the machine's identification and its intended usage. Next, the document details the team involved, clearly describing each member's expertise, responsibilities, and specific roles during the assessment. This ensures accountability and demonstrates that a diverse, competent team has carried out the risk assessment. Following this, the methodology used for the risk assessment is clearly described. This section explains the assessment process, commonly based on ISO 12100, and explicitly defines terms such as severity, likelihood, and the criteria used for categorizing risk levels. It also includes a clearly illustrated risk matrix, providing clarity on how risk levels, low, medium, high, are determined. The document then moves on to hazard identification and risk evaluation. Each hazard identified is clearly described, including a concise hazard description, the operational context, the initial likelihood and severity ratings, and the resulting overall risk level. This is typically presented in an organized tabular format for clarity and ease of reference. Once risks are identified, the document specifies risk reduction measures and safety requirements. This section details the recommended or implemented protective measures, the required safety performance level or SL rating, safety devices selected, and any required operational procedures or operator training. A section on residual risk assessment follows, documenting any remaining risks after protective measures are implemented. This demonstrates clearly whether these residual risks are acceptable or if additional measures or justifications are required. The document also includes a validation and verification plan, clearly outlining methods and timelines for validating the effectiveness of safety measures. It specifies test methods, acceptance criteria, individuals responsible for carrying out the validation, and documentation requirements for evidence. References and supporting documentation are included next, clearly listing all standards referenced: ISO 12100, ISO 13849, IEC 62061, Machinery Directive, and providing supporting documents such as safety calculations, test reports, supplier certificates, and detailed component specifications. Finally, the document concludes with a formal review and approval section. This is signed off by responsible personnel or management, formally indicating acceptance, approval, and commitment to the documented risk assessment and resulting safety measures. 7.6 Safety Summary. Compliance with electrical, safety, and regulatory standards is fundamental in the design of automation systems. Controls engineers must clearly understand how to practically apply key standards, including EN 60204-1, ISO 13849-1, IEC 62061, and IEC 61439, to select correct hardware architectures, define required performance levels P, L, or safety integrity levels SIL, and choose suitable safety-rated components. Effective automation design requires diligent attention to risk assessments, appropriate safety measures, clear component specification, and thorough validation. Comprehensive, clearly documented safety designs and procedures not only ensure compliance with legal requirements and industry best practice, but also result in safer, more reliable machinery, safeguarding operators, and enhancing long-term system performance and maintainability. 8. Control systems and programming. Control systems are the foundation of industrial automation, integrating hardware and software to ensure precise, reliable, and efficient machine operation. These systems connect PLCs, HMIs, sensors, actuators, and industrial networks to execute automated processes while maintaining safety and performance. Effective design and programming are essential for system maintainability, scalability, and troubleshooting. Programming transforms hardware into intelligent, responsive systems. Using IEC 61131-3 languages like ladder diagram LD, structured text ST, and function block diagram FBD, engineers develop structured, modular, and efficient code to enhance reliability and flexibility. Industrial networking further enables real-time communication between controllers, field devices, and supervisory systems using protocols such as Profinet, Ethernet IP, and OPC UA. Secure network design and compliance with cybersecurity standards like IEC 62443 are critical for protecting connected automation systems. Beyond functionality, automation systems must meet strict safety and regulatory standards. Compliance with ISO 13849 and IEC 62061 ensures the implementation of reliable emergency stops, interlocks, and fail-safe mechanisms to protect operators and equipment. This section explores best practices in control system design, programming, industrial networking, and integration with modern manufacturing systems. By applying structured methodologies and adhering to industry standards, engineers can develop automation solutions that are robust, efficient, and adaptable to future demands. 8.1 Software development. Software forms the core intelligence of control systems. The controls engineer is responsible for writing, maintaining, and optimizing software code to ensure reliability, readability, and maintainability.
8.1.1 PLC programming.
PLC programming is a critical aspect of control system software development. It requires an organized and systematic approach to ensure systems operate predictably and reliably. Experienced controls engineers must consider the IEC 61131-3 standard, which defines 5 programming languages specifically designed for programmable logic controllers, PLCs. Each language is suitable for particular types of applications, and while any language can technically be used for almost any task, choosing the correct one enhances readability, maintainability, and efficiency of control system software. Below are detailed explanations of each language, with practical recommendations for their usage, including their specific advantages and disadvantages. 8.1.1.1 Ladder Diagram LD. Ladder Logic, or LD, is a graphical programming language defined by IEC 61131-3 that visually represents control logic in a format similar to traditional electrical relay schematics. Its visual structure mimics rungs on a ladder, with logical conditions connected from left to right and resulting actions or outputs placed on the right-hand side. Because of its resemblance to conventional relay wiring diagrams, ladder logic remains one of the most widely used programming languages in industrial automation, particularly in environments where maintenance teams and technicians are heavily involved in day-to-day troubleshooting and system adjustments. Ladder logic is especially recommended for discrete and sequential logic control applications, including common industrial tasks such as motor start-stop sequences, conveyor systems, packaging machines, and simple interlocking processes. It is also widely used for safety-related circuits, such as emergency stop systems, mechanical interlocks, and safety relay arrangements. Furthermore, ladder logic is often employed when retrofitting older relay-based systems, providing a clear and easily understood way to transition from hardwired logic to PLC-based control without losing visibility or maintainability. One of the primary advantages of ladder logic is its highly intuitive visual representation, which makes it easy for both engineers and maintenance personnel to interpret and understand system behavior. Because of its graphical nature, ladder logic is particularly effective for simple to moderately complex control sequences that rely on binary logic, on-off, true, false, and direct device interactions. Its universal acceptance and long-standing history in industrial environments make it a safe and reliable choice for many standard automation tasks, and it remains widely supported across nearly all PLC brands and platforms. However, ladder logic also has limitations that controls engineers must consider. Highly complex algorithms, extensive mathematical operations, and advanced data manipulation tasks are difficult to represent clearly and concisely in ladder logic. As system complexity grows, ladder programs can become cumbersome, sprawling across many rungs and screens, which makes maintaining and updating the logic more challenging over time. Additionally, ladder logic offers limited scalability for applications requiring advanced functionality, such as dynamic data structures, complex array handling, or sophisticated control algorithms. In such cases, structured text, ST, or function block diagram, FBD, may be more suitable. Given these strengths and limitations, ladder logic should be used primarily in applications that involve discrete control, safety logic, simple machine sequences, or replacement of traditional relay-based control systems. Its straightforward visual nature makes it ideal for situations where the clarity and ease of troubleshooting by maintenance teams are of paramount importance. Nevertheless, for more advanced control tasks, ladder logic is often complemented by other IEC 61131-3 languages within the same project to leverage the best features of each language depending on the task. 8.1.1.2 Structured Text, ST. Structured text is a text-based high-level programming language defined by IEC 61131-3 that closely resembles traditional computer languages such as Pascal or C. In Siemens systems, this language is referred to as SCL, Structured Control Language, but functionally it is equivalent to structured text used in other platforms. Regardless of naming, SCL and ST follow the same principles and offer the same capabilities as defined in the standard. Structured text is particularly well suited for handling complex, algorithmic, and data-intensive programming tasks that would be difficult or inefficient to represent using graphical languages. It is commonly used for developing control logic, involving advanced mathematical operations, intricate algorithms, and sophisticated calculations. This includes tasks such as implementing precise control loops, performing statistical analysis, sorting and filtering large datasets, and handling structured data transformations. One of the key strengths of structured text, SCL, is its support for modular programming, which allows engineers to develop reusable code using libraries, user-defined functions, and function blocks. This approach greatly enhances maintainability and scalability of control system software, especially in large or complex automation projects. Structured text is also widely used for advanced process control strategies, including the creation of custom PID loops, dynamic set point adjustments, and integration of artificial intelligence, AI, or machine learning models for adaptive control and real-time optimization. Among its advantages, structured text is highly versatile for implementing sophisticated logic. It allows for efficient use of conditional statements, loops, and complex data structures such as arrays, structures, and user-defined types. This capability makes it easier to write clear, structured, and modular code, supporting robust software design methodologies suitable for modern, scalable automation systems. However, structured text, SCL, is generally less intuitive for maintenance technicians and plant operators without programming experience. Unlike graphical languages such as ladder logic, which are visually accessible and easier to follow for field personnel, structured text can be more challenging to read and troubleshoot without proper training. Additionally, developing and maintaining structured text code requires skilled programmers who are proficient in both the language and the control system domain. For these reasons, structured text, SCL, is recommended for applications involving complex machine control, batch processes, data processing, and advanced calculations, particularly where system clarity, modularity, and scalability are essential. It is especially powerful when developing solutions that require high-level logic and data manipulation, making it a preferred choice for engineers working on advanced industrial automation systems within Siemens environments and beyond. 8.1.1.3 Function Block Diagram FBD. Function Block Diagram FBD programming uses graphical blocks to represent logical or mathematical functions, which are interconnected by signal lines to define the flow of data and control. This method is particularly effective for continuous process control and signal processing applications, where visualizing the interaction of various control elements is essential. One of the key advantages of function block diagram programming is its intuitive visual representation of signal processing flows and continuous control loops, such as proportional integral derivative PID loops. The graphical nature of FBD makes it easier to understand and follow the flow of control logic, especially for those working with analog signals or complex process control systems. It is ideal for handling analog signals, performing real-time calculations, and automating continuous processes where clear mapping of signal pathways and control actions is beneficial. However, function block diagrams can become visually complex and difficult to interpret when dealing with highly intricate logic or when a large number of interconnected functions are required. In large systems, the diagrams may become cluttered, making troubleshooting and maintenance more challenging compared to more linear or modular languages like ladder logic or structured text. Function block diagram programming is best suited for process control applications such as chemical dosing systems and temperature control loops. It is highly effective in continuous systems that require signal processing, filtering, or mathematical operations, and in situations where a visual representation of process variables and control flows enhances understanding and validation of system behavior. 8.1.1.4 Sequential Function Chart SFC. Sequential function charts, SFC, provide a graphical method to define control sequences in a clear and structured way. SFC represents sequential processes as a series of states and transitions, making it easy to visualize machine states, logical progression, and process flows. This structured approach makes SFC particularly well suited for handling complex or sequential logic, where each stage of a process needs to be explicitly defined and controlled. One of the key advantages of SFC is that it facilitates easy troubleshooting and debugging, as engineers and technicians can clearly see the step-by-step progression of system states and transitions during machine operation. This makes it ideal for batch processes or multi-stage assembly operations where clear control over each stage is required. However, SFC is generally less suitable for applications involving purely discrete or combinational logic that do not follow a well-defined sequence, such as basic start-stop control or interlocks. In addition, SFC can become complicated if the system involves many branching paths, parallel sequences, or highly dynamic processes, which can make the charts difficult to manage and interpret. Sequential function charts are best applied in batch production systems where adherence to ISA 88 principles is required, as well as in complex sequential manufacturing lines, such as automated assembly stations or packaging lines. They are especially useful in situations where having clearly defined machine states improves troubleshooting, validation, and operator understanding of the process flow. 8.1.1.5 Instruction List, IL, deprecated in newer standards provided for completeness. Instruction List is a low-level text-based programming language that closely resembles assembly language. Historically, it was valued for its high execution speed and very compact code footprint, making it suitable for applications where processing efficiency was critical. However, Instruction List is notoriously difficult to read, understand, and maintain, even for experienced engineers and technicians. As control systems have evolved, Instruction List has largely been replaced by more modern languages such as structured text, which offer similar capabilities but with improved readability and maintainability. Many major PLC manufacturers have now removed support for Instruction List or actively discourage its use in new projects due to these limitations. For these reasons, Instruction List should be used sparingly and only when absolutely necessary, such as when working with legacy hardware that mandates its use, or in specific cases where extreme code compactness is required. For all modern designs, it is strongly advised to avoid Instruction List in favor of more maintainable and standardized languages like ladder logic, structured text, or function block diagram. 8.1.1.6 General Recommendations for Language Selection. While it is technically feasible to implement any given functionality using any IEC 61131-3 language, careful selection significantly impacts maintainability, readability, and ease of troubleshooting. Recommended general practices include: use ladder logic for safety-critical logic, discrete control, and simple sequencing for ease of maintenance and visual troubleshooting. Choose structured text for complex algorithms, calculations, conditional logic, and modern modular software design approaches. Adopt function block diagrams for process-oriented applications involving continuous control, analog signal processing, and graphical representation of complex interactions. Employ sequential function charts to manage batch processes, clearly defined sequential states, or complex system operations requiring structured state transitions and step-by-step visibility. 8.1.1.7 Summary and best practice recommendations.
While it is possible to use any IEC 61131-3 language for almost any automation task, each language has distinct strengths that best align with particular types of tasks. Experienced controls engineers maximize their system's efficiency and maintainability by choosing the language best suited to the application's complexity, safety requirements, operator familiarity, and long-term maintenance needs. A hybrid approach, combining several IEC languages within a single project, can often offer the most balanced solution, leveraging the advantages of each language within its most appropriate context.
8.1.2 Modular and Structured Code, ISA 88 and ISA 95. Modular and structured programming is essential for developing control system software that is reliable, maintainable, and scalable. As automation systems grow in complexity, unstructured or ad hoc programming approaches quickly become unmanageable, difficult to troubleshoot, and prone to errors. To address this, controls engineers should adopt modular programming architectures, which break down complex systems into smaller reusable components. Two internationally recognized standards, ISA 88 and ISA 95, provide frameworks for developing structured control software that supports modularity, standardization, and integration across both the factory floor and enterprise systems. ISA 88, originally developed for batch process control, introduces the concept of breaking a control system into modular equipment phases, units, and procedural elements. Although it was designed for batch processes, the underlying principles of ISA 88 are now widely applied in discrete manufacturing and continuous processes. Following ISA 88, control systems are organized into phases, individual operations or sequences, units, physical or logical equipment, and modules, reusable software objects. This modular approach allows engineers to write reusable function blocks or classes to represent devices such as valves, motors, and pumps, which can be instantiated multiple times throughout the system with standardized behavior and diagnostics. For example, instead of writing separate code for every valve in a system, a single valve module can be created, encapsulating all necessary control logic, interlocks, fault handling, and feedback. Each valve instance can then be configured with unique parameters, e.g., tag names, addresses, greatly improving maintainability and scalability. ISA 95 extends this structured thinking beyond the control system itself, focusing on integration between control systems level 2 and enterprise systems level 4, such as MES manufacturing execution systems and ERP enterprise resource planning. ISA 95 defines clear interface layers and data models to ensure that control systems can seamlessly exchange information with higher level business and production systems. By following ISA 95 principles, controls engineers ensure that the PLC and SCADA systems they develop are not isolated but are designed to fit into the larger operational and enterprise context, enabling real-time production tracking, quality management, and resource planning. Applying modular and structured coding principles in line with ISA 88 and ISA 95 delivers several critical benefits. Improved code. Readability, breaking the system into well-defined modules, each responsible for specific equipment or functions, makes the overall control logic easier to read, understand, and modify. Engineers working on different parts of the system can quickly grasp how each module operates without navigating through tangled monolithic code. Code reusability and standardization. Reusable software modules ensure consistency in how similar devices, e.g., motors, valves, drives, are controlled. This reduces engineering time, minimizes errors, and improves the reliability of the system. Standardization also simplifies training for operators and maintenance personnel, as devices behave predictably across the plant. Scalability and flexibility. A modular architecture makes it much easier to expand or modify systems as production needs change. New equipment can be added by instantiating existing modules, and new control sequences can be created by combining standard phases and units without rewriting core logic. Easier troubleshooting and diagnostics. With modular code, individual modules can include built-in diagnostics and alarms. When a fault occurs, the system can identify exactly which instance of a device is at fault, improving fault isolation and reducing downtime. Enterprise integration and data handling. By following ISA 95, control systems are designed with structured data models and communication interfaces, e.g. OPC UA MQTT, RESTAPIS, that facilitate smooth data exchange with MES and ERP platforms. This enables real-time monitoring of production, automatic generation of production reports, and seamless coordination of production orders. In practice, implementing modular and structured code aligned with ISA 88 and ISA 95 means developing a library of standardized function blocks, user-defined data types, and interfaces, which can be reused across different machines and projects. For large organizations, these libraries may form part of a corporate standard, ensuring that all systems share a common software architecture, simplifying maintenance, and enabling smoother integration of new equipment over time. Ultimately, modular and structured programming is not just about writing better code, it is a strategic approach to building robust, future-proof automation systems that can adapt to changing demands, integrate seamlessly with business operations, and deliver long-term value to manufacturers. 8.1.3 Robust Diagnostics and Error Handling. 8.1.3.14.2.3 Robust Diagnostics and Error Handling. Robust diagnostics and error handling are critical but often overlooked elements of control system design. Due to time constraints, project deadlines, or underestimating the importance, many engineers either skip this step or implement only basic fault handling. However, failure to properly implement diagnostics and error handling routines leads to systems that are difficult to maintain, troubleshoot, and operate, resulting in increased downtime, reduced safety, and higher operational costs.
Properly designed diagnostic logic enables a system to detect and react to abnormal conditions, such as sensor faults, actuator malfunctions, and communication failures, before they cause process disruption or unsafe situations. It allows operators and maintenance personnel to respond efficiently, guided by clear and actionable information presented via HMIs or SCADA.
8.1.3.2 Sensor fault detection and validation. One essential area of robust diagnostics is sensor fault detection. A simple example is programming logic to check if a sensor has been unplugged, failed, or is reading invalid data. This can be done by implementing range checks. For instance, if an analog sensor, e.g. 4 to 20 mA pressure transmitter, provides a reading outside its expected operating range, such as below 3.5 mA or above 21 mA, this can indicate a broken wire, sensor failure, or power issue. For digital sensors, such as proximity switches or photo eyes, pulse timing or consistency checks can detect if the sensor has stopped toggling as expected during a machine cycle, indicating mechanical jamming or sensor malfunction. Engineers should write PLC logic to evaluate sensor status against known expected behaviors and set fault bits when anomalies are detected. Example: if a conveyor belt is running and a proximity sensor that detects passing boxes does not toggle within an expected time window, a fault should be raised indicating a probable jam or sensor issue.
8.1.3.3 Process value plausibility checks. Beyond simple range checks, plausibility checks compare multiple sensor inputs to verify if they make sense together. For example, a system monitoring a tank level should compare inflow valve status and level change. If a valve is open but level does not rise, a fault may exist in the valve actuator, flow path, or level sensor itself.
Such cross-validation techniques require controls engineers to fully understand the process dynamics and identify where relationships between signals can be monitored for inconsistency. 8.1.3.4 Communication loss detection. Modern PLC systems often rely on remote I/O distributed drives and intelligent sensors connected via industrial networks such as Profinet, Ethernet IP, or I/O Link. Communication diagnostics are crucial to detect and handle issues such as loss of connection to remote I/O racks, timeouts from variable frequency drives, VFDs or servos, failure of safety communication, e.g., Profi-Safe or CIP safety links. Effective diagnostics must monitor network status bits, cyclic error codes, and heartbeat or watchdog timers, triggering alarms or initiating safe shutdowns when critical communication paths are lost. Example: a VFD used in motion control should be continuously monitored for communication timeouts. If a timeout occurs, the system must raise an error and stop the motion in a controlled manner using safe torque off STO signals if necessary. 8.1.3.5 Actuator and output feedback validation. Actuator diagnostics, such as for solenoid valves, contactors, or motor starters, should validate that the commanded output produces the expected result. For example, if a valve is commanded open, a feedback switch should confirm that the valve has reached the open position within a reasonable time. If not, the system should issue a valve failure alarm. Without this validation, failures such as jammed valves, faulty solenoids, or electrical wiring issues may go unnoticed until they cause production or safety issues. Example: when starting a pump via a contactor, an auxiliary contact should confirm that the contactor has pulled in successfully. If the contactor feedback does not match the command, a pump start fault alarm should be generated, and the system should prevent further actions until resolved. 8.1.3.6 Explicit error, messaging and alarming. All diagnostic routines should be tied to clear, unambiguous alarm messages presented to operators through HMIs and SCADA systems. Vague alarms like machine fault are of little use. Instead, alarms must provide specific guidance, such as sensor X out of range, check wiring, or valve Y failed to open within timeout, possible mechanical jam.
Furthermore, alarms should be categorized based on severity, e.g., critical, warning, informational.
Include time-stamped history to track recurring issues. Support event logging to aid in root cause analysis. Trigger automated responses if necessary, e.g., stop dangerous machine motion on a critical fault. Following ISA 18.2 alarm management principles, engineers should ensure that alarms are actionable, prioritized, and free from alarm flooding, where too many simultaneous alarms overwhelm operators.
8.1.3.7 Failsafe and controlled responses. Beyond detection and notification, error handling should define failsafe responses to prevent equipment damage or personnel injury. For example,
if a critical sensor fails, the system should enter a safe state, e.g., shutting off a motor or closing a valve. If communication with a remote safety device is lost, the safety system should force an emergency stop or bring equipment to a controlled stop. If an actuator does not respond as commanded, the system should prevent moving to the next step in a sequence to avoid potential collisions or product defects. All error handling routines should be tested thoroughly during commissioning, using simulated fault conditions to verify correct system responses. 8.1.3.8 Why engineers avoid diagnostic routines and why they shouldn't. Despite the critical importance of diagnostics, many engineers omit this part of the programming due to tight project deadlines, cost pressures, or underestimating its value. Diagnostics are often seen as extra or nice to have, rather than an essential part of system functionality. However, failure to implement robust diagnostics inevitably leads to longer downtime, difficult fault finding, and potential safety risks in live operation. Well-implemented diagnostics reduce maintenance effort, increase system uptime, and improve operator confidence. As automation systems become more complex, especially with distributed networks and smart devices, diagnostics are no longer optional, but an integral part of professional high-quality control system design. 8.1.3.9 Diagnostic Summary. Robust diagnostics and error handling form the backbone of safe, reliable, and maintainable automation systems. By writing intelligent diagnostic routines, covering sensor faults, actuator validation, and communication integrity, and linking them to clear and actionable alarms, controls engineers can dramatically improve system performance and resilience. Although often overlooked due to time pressures, diagnostic programming should be treated as a core component of any professional automation project, ensuring both technical excellence and long-term operational success. 8.1.4 Alarm Management. Effective alarm management is a crucial part of control system design and directly impacts plant safety, operator response, and overall system reliability. Poorly designed alarm systems can overwhelm operators, delay corrective actions, and contribute to unsafe situations. A structured and systematic approach to alarm management ensures that alarms serve their intended purpose to notify operators of abnormal conditions requiring timely intervention without creating unnecessary distractions or alarm flooding. Modern control systems should integrate alarms directly within the PLC logic, ensuring that the alarms are aligned with the system's real-time state and behavior. These alarms must be clearly defined, prioritized, and presented to operators in a way that is actionable, understandable, and relevant to current plant conditions. 8.1.4.1 Alarm Classification and Prioritization. All alarms should be categorized by severity to help operators focus on what requires immediate action and what can be handled later. Typical categories include critical alarms. These indicate serious faults or hazardous conditions requiring immediate operator action to prevent harm to personnel, equipment, or product. Examples include loss of safety critical sensors, actuator failures that prevent safe shutdown, or system overpressure conditions. Critical alarms often require automatic system responses, such as emergency stops or fail-safe shutdown sequences. Warning alarms. These indicate non-critical faults or abnormal conditions that may require attention but do not pose an immediate risk. Warnings provide operators with early notification, so that corrective action can be planned. Examples include a temperature approaching a limit, slow response from a valve, or reduced pressure in a system. Informational alarms, advisories. These provide status updates or non-urgent messages. They may indicate changes in machine state, maintenance reminders, or less critical issues that do not immediately affect production. Examples include tank refilling complete, filter maintenance due, or temporary communication delays that are self-recoverable. By categorizing alarms, operators can quickly identify and prioritize actions, focusing first on what is urgent and critical to safety and production. 8.1.4.2 Avoiding alarm, flooding and nuisance alarms. One of the most common issues in poorly designed alarm systems is alarm flooding, where a single fault condition generates dozens of alarms, overwhelming operators and obscuring the root cause. Effective alarm management must limit alarms to what is necessary for effective response, and avoid generating redundant or secondary alarms that do not require direct action. Techniques to prevent alarm flooding include grouping related alarms under a common cause or master alarm, e.g., conveyor line fault, see details. Using alarm suppression or masking to hide non-relevant alarms during certain operating modes, e.g., suppressing flow alarms when a pump is intentionally off. Rate limiting alarms that repeat frequently within short time frames to avoid continuous retriggering. Conditional alarms that only trigger when their context is valid, e.g., only generating a low flow alarm when a valve is commanded open, not when closed. Preventing nuisance alarms also includes ensuring that alarms are based on well-defined set points and process conditions, not transient fluctuations. For instance, applying time delays or hysteresis prevents alarms from triggering during brief deviations that self-correct. 8.1.4.3 Clear and actionable alarm messages. Every alarm presented to the operator should be clear, concise, and actionable. Vague or generic alarm messages like fault detected are not useful. Instead, alarms should specify exactly what the problem is and what the operator should do next. For example, rather than displaying sensor fault, the alarm should specify pressure sensor P T101 out of range, check wiring and sensor power supply. Key information for effective alarms includes a description of the issue, what went wrong, component identification, which device is affected, possible cause or action, what to check or do next, severity level, critical, warning, informational. Alarm integration with HMI and SCADA systems. Alarms should be clearly displayed on HMIs and SCADA systems in a way that directs operator attention without overwhelming them. Features of a well-integrated alarm system include color-coded prioritization, e.g., red for critical, amber for warnings, blue-gray for informational. Time-stamped alarm history for post-event analysis and troubleshooting. Acknowledge and reset functions that allow operators to confirm receipt and response to alarms. Alarm summary and filtering views that allow operators to focus on active alarms relevant to their area or role. Trending and analysis tools to review alarm frequency and identify recurring issues for continuous improvement. Following guidelines such as ISA 18.2, Management of Alarm Systems for the Process Industries, ensures that alarms are systematically designed, documented, and tested. 8.1.4.5 Best Practice Example: Alarm for sensor failure. Consider a 4 to 20 milliamp level transmitter used to monitor tank level. A well-designed alarm strategy would include critical alarm, level transmitter LT205 signal lost, reading less than 3.5 milliamps, check wiring and transmitter power. Triggers an immediate tank shutdown sequence if level monitoring is essential for safety. Warning alarm, level approaching maximum, 85% of tank capacity, gives operator time to adjust flow or switch tanks. Information alarm, level stable for last 24 hours. No inflow detected. Used for maintenance review, not requiring urgent action. Each of these alarms is context-specific, relevant, and includes suggested operator actions. 8.1.4.6 Alarm Management Summary. Comprehensive and well-structured alarm management is essential for safe and efficient operation of industrial automation systems. By classifying alarms properly, preventing alarm flooding, writing clear and actionable messages, and integrating alarms effectively into operator interfaces,
Controls engineers ensure that alarms function as intended, as critical tools to guide and protect both personnel and processes. Proper alarm management improves response times, reduces downtime, and forms a cornerstone of professional, compliant, and maintainable control system design.
8.1.5 Code Optimization and Resource Management. Code optimization and resource management are critical aspects of professional PLC software development, especially as control systems become more complex and resource constrained. While it is often tempting to focus only on achieving functional logic that works, poorly structured and inefficient code can lead to serious issues such as slow scan times, delayed system response, unexpected faults, and even safety risks in high-speed or critical applications. Therefore, writing efficient, structured, and optimized code should be considered a fundamental engineering practice, not an optional enhancement. Optimizing PLC code ensures that control systems execute within predictable timeframes, use memory resources efficiently, and remain scalable for future expansions. This is particularly vital in applications with tight cycle times, safety-critical functions, or real-time motion control, where even minor delays can lead to performance degradation or unsafe operation. 8.1.5.1 Efficient Code Structure and Logical Flow. One of the first principles of code optimization is to structure the PLC code logically and hierarchically, following a modular approach. Dividing code into well-defined sections, e.g. input handling, safety logic, process sequences, outputs, makes it easier to understand and maintain while preventing duplication of logic. Reusable function blocks FBS, functions FCS, and user-defined data types UDTS should be used extensively to encapsulate repeatable operations, e.g. motor control valve sequencing safety checks. Instead of repeating similar control logic for each device, a single function block parameterized with device-specific tags and parameters improves both code clarity and execution efficiency. This approach also makes fault finding and future upgrades significantly easier, as changes can be made in one place and applied system-wide. Example, rather than writing independent start-stop logic for 20 motors, a motor control function block can handle all related logic, start, stop, fault feedback, overload detection, and be instantiated for each motor with its unique addressing.
8.1.5.2 Optimizing scan times and loop efficiency.
In many industrial applications, PLC scan time, cycle time, is a critical parameter. A long or inconsistent scan time can lead to delayed reactions, inaccurate timing, and failure to meet process requirements. Controls engineers must write code that minimizes unnecessary operations within each scan cycle. Some key techniques to manage and optimize scan time include minimizing cyclic calculations. Avoid repetitive mathematical operations, especially floating point calculations, inside fast-running control loops. Where possible, move heavy calculations to slower-running background tasks or execute them conditionally.
Conditional execution. Use enabling conditions to execute code only when necessary. For example, instead of continuously calculating a PID loop when a machine is idle, check if the machine is in the run state before running the PID block.
Efficient use of loops. Avoid unnecessary or infinite loops within the PLC. If iterative logic is required, carefully control the number of iterations and ensure that loop conditions are valid and bounded. Avoid blocking instructions. Some instructions, particularly communication or complex mathematical functions, may block scan progression while waiting for a response. Use asynchronous communication and verify that functions are non-blocking where real-time performance is needed. PLC systems have finite memory for storing code, variables, and buffers. Poorly managed data structures can quickly exhaust available memory, leading to compile errors, limited functionality, or sluggish operation. Proper data management is key to maintaining a healthy system. Use of user-defined data types, UDTs. Defining custom structured data types to group related variables, e.g. all status and command data for a motor, reduces the number of individual tags and improves code readability. It also enables easier expansion and modification of device parameters.
Eliminating redundant variables. Review and remove unused or duplicated variables to free up memory. This prevents unnecessary memory occupation and improves performance, especially in systems where data exchange across networks e.g. OPC-UA, Profinet, may be affected by tag count.
Efficient array and buffer handling. Use arrays and indexed access for sets of similar data, e.g. sensor arrays, production counters, rather than individual variables for each instance. Ensure arrays are dimensioned correctly. Large unused arrays waste significant memory space. Minimizing retention. Retained, persistent variables consume non-volatile memory. Only data that must survive power cycles, e.g. production counters, configuration settings, should be declared as retained. Regular process data should use volatile memory to minimize wear on flash-based PLC storage and reduce cycle load. In distributed and networked systems, inefficient communication logic can severely impact both the PLC's performance and the network itself. Controls engineers must ensure that communication cycles are managed appropriately. Only essential data is transmitted at high rates. Non-critical information can be sent at slower intervals to avoid network congestion. Use of triggered communication rather than continuous polling. Event-based communication, e.g. sending data only on value change, reduces unnecessary data flow, improving both PLC and network performance. Buffering and batching data, grouping multiple values into a single transmission, e.g. as a UDT or array, instead of sending individual values, can greatly reduce overhead and improve consistency of transferred data. In high-speed applications such as robotics, packaging, high-speed assembly, and motion control, deterministic scan times are crucial. Inconsistent or slow code execution can lead to motion inaccuracies, missed sensor readings, or timing faults. For safety-critical systems, such as those governed by ISO 13849 or IEC 62061, consistent and timely response to safety signals, e.g. emergency stops, light curtains, interlocks, is essential. Poorly optimized code that introduces variable delays can undermine the integrity of safety functions, resulting in non-compliance and potential hazards. 8.1.5.6 Common mistakes in code optimization. Despite its importance, optimization is often overlooked or improperly executed. Common mistakes include
Writing large blocks of unstructured code without modular separation, making logic hard to follow and maintain.
Using excessive or unnecessary subroutines, causing repeated execution of non-critical logic. Placing complex calculations or diagnostics in fast scan tasks instead of offloading to slower background processes. Failing to monitor scan time performance during development and commissioning, only discovering issues after system faults occur. 8.1.5.7 Code Optimization Summary.
Code optimization and resource management are essential practices that ensure control systems are not only functional, but also efficient, reliable, and scalable. Through careful structuring of logic, efficient memory, and data management, and minimized processing load, controls engineers can deliver PLC programs that meet the demanding needs of modern industrial automation, including high-speed, safety-critical, and networked systems. Failing to prioritize optimization may not immediately prevent a system from running, but it will almost certainly result in long-term performance degradation, maintenance headaches, and limited system flexibility. Therefore, optimization should be considered a core responsibility of any professional controls engineer, embedded within the development process from the earlier stages of system design.
8.1.6 HMI SCADA Development. 8.1.6.1 Designing Effective HMIs. ISA 101. HMI Human Machine Interface and SCADA Supervisory Control and Data Acquisition. Systems form the primary interface between industrial control systems and operators, making their design critical to both operational efficiency and safety. A well-designed interface enables operators to monitor processes in real time, make informed decisions, and respond quickly to abnormal conditions, while a poorly designed system can lead to confusion, delays, and errors that risk equipment, product, and personnel.
Modern HMI/SCADA design must balance simplicity and functionality, presenting all necessary information without overwhelming the user. Following industry standards, such as ISA 101, human-machine interfaces for process automation systems is essential to ensure that interfaces are consistent, intuitive, and effective across industrial environments.
8.1.6.2 Adherence to ISA 101 HMI Design. Following ISA 101 guidelines ensures that HMI systems are designed based on structured and proven principles rather than ad hoc or operator-specific preferences. ISA 101 mandates the use of clear screen layouts, consistent navigation, effective use of color, and prioritized alarm displays. Operators should be able to instantly identify machine states, diagnose issues, and execute safe interventions without ambiguity or hesitation. Screen layouts should be logically organized, avoiding clutter while ensuring that all critical information is readily visible. Navigation between screens must be consistent and intuitive, using standard symbols and terminology throughout the system. By adhering to these best practices, engineers help ensure that HMIs enhance situational awareness and contribute to safer, more reliable operations. 8.1.6.3 Visual Hierarchy and Information Clarity.
A crucial element of HMI/SCADA design is visual hierarchy, ensuring that the most critical information stands out and draws immediate attention. Information should be organized so that key process parameters, alarms, and safety critical indicators are prominent, while secondary or informational data is presented in a less obtrusive manner.
Color usage must be consistent and meaningful. Red should be reserved exclusively for critical alarms or dangerous conditions. Amber, yellow, should indicate warnings that require operator awareness but are not immediately hazardous. Green should represent normal, healthy system operation. Gray or muted colors are appropriate for inactive states or background elements to prevent unnecessary visual noise. Text and numeric data should be clear, legible, and appropriately sized, with sufficient contrast to ensure readability under various lighting conditions. Graphical elements such as tanks, valves, and motors should be designed with simple, unambiguous symbols that reflect real-world devices. 8.1.6.4 Effective alarm presentation. Alarms must be clearly displayed, prioritized, and actionable. Alarms that are hidden, non-specific, or poorly prioritized can lead to missed critical events or operator desensitization to alarms. Alarm fatigue. Each alarm should include a precise description of the issue, identification of the affected equipment or process, recommended corrective actions so that operators understand what needs to be done, a severity level indicating whether immediate action is required, critical, or if the situation should be monitored, warning, informational.
Alarm suppression and filtering should be implemented to prevent overload during certain operating modes, e.g., maintenance, and alarm rationalization should be used to ensure only meaningful alarms are presented. For example, if a process line is in standby mode, flow alarms related to inactive pumps should be suppressed until the system is running.
Visual and audible indicators must be used thoughtfully. For example, critical alarms may require flashing red visuals and a unique sound, whereas informational alarms might use a simple text display without sound. 8.1.6.5 Intuitive Operator Interaction. Operator interactions with HMI/S CADA systems must be designed to minimize error risk and improve efficiency. All input fields, buttons, and controls must be clearly labeled and located logically relative to the process being controlled. Complex actions such as starting a batch process or initiating a controlled shutdown should be supported by step-by-step prompts or checklists to prevent mistakes. Validation routines should be in place to prevent incorrect inputs, for example, disallowing set points outside of safe operating ranges, or confirming that preconditions are satisfied before allowing a machine to start. For critical actions such as stopping production or resetting alarms, confirmation prompts should be used to ensure the operator intends to perform the action, reducing the likelihood of accidental commands. Interactive elements should be responsive and provide immediate feedback, such as changing color when a button is pressed or showing a progress indicator for ongoing operations. 8.1.6.6 Integration with PLC Diagnostics.
An effective HMI/SCADA system should present real-time diagnostics directly from the PLC, allowing operators and maintenance personnel to quickly identify faults and their causes. Diagnostics may include sensor failures, e.g., out-of-range signals, broken wires.
Actuator feedback mismatches, e.g., valve command not matching position feedback. Communication losses with remote I/O or drives. Fault codes from variable frequency drives or servo controllers. Rather than generic machine fault messages, Diagnostics should pinpoint the specific issue, such as pump 3 motor overload trip or conveyor 2, sensor S104 disconnected. Direct linking of alarms to diagnostic screens allows for one-click access to detailed fault information, wiring diagrams, or troubleshooting instructions, significantly reducing downtime. 8.1.6.7 Secure Communication and Authentication. Security is a growing concern in modern industrial control systems. HMI and SCADA systems must implement role-based access control, RBAC, where users are granted permissions based on their responsibilities. For example, only authorized personnel can adjust set points or acknowledge critical alarms. User authentication should require strong passwords and ideally multi-factor authentication, MFA, for sensitive operations. All system access should be logged in an audit trail, recording who did what and when, vital for traceability and compliance with safety standards such as IEC 62443. Communications between HMIs, SCADA, PLCs, and remote systems must be encrypted and protected using secure protocols such as OPC UA Secure, HTTPS, or VPN-based remote access. Plain unencrypted communication, especially over wireless or external connections, introduces unacceptable risks in modern industrial environments. 8.1.6.8 HM, a summary. HMI and SCADA systems form the human connection to automation, and their design must be approached with the same level of discipline and engineering precision as the control logic itself. By adhering to ISA 101 design principles, establishing clear visual hierarchies, integrating robust alarm management, enabling intuitive operator interactions, embedding real-time diagnostics, and enforcing cybersecurity measures, controls engineers create interfaces that are safe, effective, and operator-friendly. Well-designed HMIs not only improve system visibility and responsiveness, but also play a critical role in ensuring operator confidence, plant reliability, and process safety. An investment in proper HMI/SCADA design is an investment in the long-term success of the entire automation system. 8.1.7 Data Integration and Analytics. Integrating PLC systems with advanced data acquisition and analytics platforms is essential for modern industrial automation. It allows manufacturers to move beyond traditional control and monitoring, enabling data-driven decision-making that enhances production efficiency, process optimization, predictive maintenance, and overall plant reliability. Controls engineers are increasingly required to design systems that do more than operate machines. They must deliver actionable insights to operators, maintenance teams, and management through real-time and historical data. This requires careful attention to system architecture, data modeling, communication protocols, and cybersecurity, ensuring that data is both meaningful and secure. 8.1.7.1 Real-time data acquisition. Real-time data acquisition is the foundation of any analytics-driven control system. High-quality, timely data from the PLC is essential for effective monitoring, control, and analysis. Controls engineers must carefully select communication protocols that match system requirements, including latency, reliability, and security. Protocols such as OPC UA, MQTT, Ethernet IP, and Profinet are commonly used to transmit PLC-generated data to SCADA systems, manufacturing execution systems, MES, and cloud analytics platforms. OPC UA and MQTT are particularly well suited for scalable cross-platform integration, supporting hierarchical data models and secure communications. In high-speed or safety-critical applications, such as motion control or real-time condition monitoring, fast deterministic data exchange is essential, often requiring dedicated protocols like EtherCAT, Profinet IRT, or Circos. Controls engineers must design data structures, e.g. UDTs, structured tags, that make data easy to map, interpret, and process across systems. 8.1.7.2 Historical trending and process analysis. Storing and analyzing historical process data is critical for long-term process optimization, fault investigation, and regulatory compliance. Data should be archived in industrial historians or SCADA databases, allowing engineers and process experts to review past performance, perform root cause analysis, and verify improvements. Examples of key data to be historically logged include process variables, temperature, pressure, flow rates, machine states and operational counters, alarms and events with timestamps, operator actions, and set point changes. The data must be structured in a way that supports efficient querying and reporting, and be accessible via dashboards or reports for process owners and managers. Proper structuring ensures that complex analyses, such as detecting gradual performance degradation or recurring faults, can be performed without cumbersome manual data review. 8.1.7.3 Advanced Data Analytics and Machine Learning. Once real-time and historical data are available, advanced analytics platforms can apply statistical analysis and machine learning algorithms to generate deep insights that would not be visible through standard monitoring. Controls engineers should facilitate the connection of PLC data to edge-based or cloud-based analytics tools, where the following advanced functions can be implemented. Predictive maintenance models that anticipate equipment failure based on trending data, e.g., vibration, temperature, motor current. Anomaly detection systems that automatically identify when processes deviate from normal behavior, triggering early alarms before actual faults occur. Optimization algorithms that adjust control parameters dynamically to improve process efficiency, e.g., adjusting PID loops based on changing load conditions. Machine learning models trained on historical data can be deployed to predict product quality issues, detect inefficient operations, or automate complex decisions that would typically require manual intervention. This is an emerging but critical area for the future of industrial control systems. 8.1.7.4 Integration with MES and ERP systems, ISA 95. Integrating PLC-generated data with manufacturing execution systems, MES, and enterprise resource planning, ERP platforms is crucial for aligning shop floor operations with business goals. Following ISA 95 standards, control systems can be designed to seamlessly share data between equipment and enterprise systems, supporting production tracking, real-time view of what is being produced, how much, and at what efficiency. Resource allocation, linking machine data with supply chain and inventory management. Quality management, feeding process and quality data into centralized databases for compliance and reporting. Downtime and performance monitoring, feeding OEE data to management systems. Using well-defined interfaces, e.g. OPC UA gateways, RESTful APIs, engineers ensure reliable, secure, and efficient data exchange that provides full visibility from the control layer to the business layer. 8.1.7.5 Condition-based and predictive maintenance. Rather than relying solely on periodic preventive maintenance, modern control systems should enable condition-based and predictive maintenance strategies. This approach involves continuously monitoring machine health parameters via sensors, vibration, temperature, pressure, electrical signals, and analyzing them for early signs of wear or failure. By integrating these signals into analytics platforms, engineers can detect degradation trends, such as increasing vibration indicating bearing wear, predict time to failure using AI models, allowing maintenance to be scheduled before breakdowns occur, avoid unnecessary maintenance on healthy equipment, reducing costs and improving asset utilization. PLC code should include local pre-processing of diagnostic signals to reduce unnecessary network traffic and enable fast local responses, e.g., shutting down a pump if pressure drops below safe limits, while more complex trend analysis can be performed in SCADA or external analytics platforms. 8.1.7.6 Cybersecurity and Data Integrity, IEC 62443. With the rise of IIoT and cloud-connected systems, cybersecurity and data integrity are now core concerns in industrial data integration. All data transmissions must be secured using modern encryption protocols and secure communication standards such as TLS, OPC-UA Secure, and VPN. Network architecture should employ segmentation, isolating control networks from business and public networks to prevent lateral movement of potential attacks. Role-based access control, RBAC, secure authentication, and audit logging are required to control who can access or modify critical system data. In industries subject to regulatory compliance, such as pharmaceuticals, food production, or energy, continuous verification of data integrity is essential. Controls engineers must ensure that any data used for reporting, regulatory submission, all quality control is accurate, traceable, and tamper-proof. Following IEC 62443 guidelines, engineers should build security into the system architecture from the start, rather than as an afterthought. 8.1.7.7 Data Integration Summary. Controls engineers today are not only responsible for writing PLC programs and HMI screens, but must also manage the full lifecycle of data, from acquisition to analytics to enterprise integration. High-quality structured data flows allow companies to unlock advanced capabilities like predictive maintenance, AI-driven optimization, and real-time production insights, giving them a competitive edge. A well-designed system requires adherence to modern standards, ISA 95, ISA 101, IEC 62443, thoughtful data architecture, efficient communication handling, and secure, robust data integration. By embedding these principles, controls engineers ensure that industrial automation systems are future-proof, efficient, and capable of delivering value beyond simple machine control. 8.2 Industrial Networking and Communication Protocols. Effective communication networks underpin modern industrial automation systems, enabling rapid data exchange, precise synchronization, and integration with enterprise-level systems. 8.2.1 Ethernet/IP, Profinet Modbus OPC UA.
Widely used industrial protocols include
Ethernet IP, Ethernet-based protocol using CIP, Common Industrial Protocol for real-time control and data collection. Profinet, real-time, deterministic Ethernet-based standard, supporting safety via ProfiSafe. Modbus TCP/IP, simple, versatile, open protocol ideal for cross-platform integration. OPC UA, platform-independent, secure data modeling protocol, enabling interoperability and Industry 4.0 applications. 8.2.2 IO-Link and Fieldbus systems.
field-level communication systems.
IO-Link, simple point-to-point communication protocol used for intelligent sensors and actuators, enabling advanced diagnostics and parameterization. Traditional fieldbus systems, Profibus DeviceNet, widely used for distributed I/O and motion control, transitioning increasingly toward Ethernet-based protocols.
8.2.3 Wireless and remote access in industry.
Wireless technologies offer flexibility and mobility. Industrial Wi-Fi IEEE 802.11, commonly used in mobile or remote monitoring applications, demands robust security, e.g. WPA3 VPN tunneling. Remote access solutions, secure gateways, and VPN-based access, enabling remote diagnostics, support, and maintenance of automation systems. Effective design of control systems, programming practices, user interfaces, and robust industrial networks provides a foundation for high-performing automation systems. By adhering to best practices, engineers deliver reliable, maintainable, and future-ready automation solutions. 9. Advanced Automation and Industry 4.0. Industry 4.0 is transforming industrial automation by integrating smart technologies, advanced data analytics, and interconnected systems to create intelligent, self-optimizing production environments. Unlike traditional automation, which relies on predefined control logic, Industry 4.0 enables machines to communicate, analyze real-time data, and adapt dynamically to changing conditions. This shift enhances efficiency, reduces downtime, and improves overall system flexibility. At the core of Industry 4.0 is the Industrial Internet of Things, IIoT, a network of smart sensors, controllers, and edge devices that collect and exchange data across industrial networks. This data drives predictive maintenance, process optimization, and digital twins, virtual representations of physical systems used for simulation, analysis, and continuous improvement. Cloud computing and big data analytics further enable manufacturers to process vast amounts of operational data, unlocking new insights for efficiency gains and cost reductions. Artificial intelligence, AI, and machine learning, ML, play a growing role in automation, providing real-time anomaly detection, automated quality inspection, and adaptive process control. AI-driven systems can predict failures before they occur, optimize production schedules based on demand patterns, and even autonomously adjust machine settings to improve efficiency. Cybersecurity becomes increasingly critical
as connectivity expands, with Industry 4.0 requiring secure network architectures that adhere to IEC 62443 and other security frameworks to protect against cyber threats and unauthorized access.
This section explores the key elements of Industry 4.0, including IIoT, smart data collection, AI-driven automation, and the role of cybersecurity in protecting interconnected industrial systems. By understanding these technologies and their practical applications, engineers can design control systems that are future-proof, scalable, and capable of driving the next generation of industrial efficiency and innovation. 9.1 Industry 4.0 and Smart Factories. Industry 4.0 represents the evolution of traditional manufacturing into interconnected systems that integrate advanced digital technologies, intelligent devices, and real-time analytics to improve productivity, flexibility, and responsiveness. It marks the shift from isolated automation islands towards fully networked and autonomous production environments. This transformation relies heavily on data-driven decision-making, predictive analytics, and machine-to-machine communication, enabling factories to operate more intelligently, efficiently, and adaptively. 9.1.1 IIoT. Central to Industry 4.0 is the Industrial Internet of Things 2OT, a network of intelligent sensors, actuators, and control systems connected through secure communication networks to cloud or edge-based analytics platforms. Unlike traditional automation, which typically uses isolated closed-loop controllers and limited local feedback, IIoT expands control systems into a broader digital ecosystem. This enables controls engineers to collect vast amounts of real-time data from virtually every element of the production line, facilitating advanced analysis, proactive decision-making, and process optimization across the entire manufacturing operation. 9.1.2 Data collection. Real-time data collection and analysis is one of the core components of IIoT-enabled automation. Sensors embedded throughout the manufacturing plant continuously transmit critical parameters such as temperature, pressure, vibration, current draw, and equipment status to centralized monitoring systems. Controls engineers must carefully select and implement secure communication protocols suited to high volumes of data transmission, including OPCUA, MQTT, Ethernet IP, and Profinet. OPCUA and MQTT, in particular, offer flexible data modeling and scalable data transmission, making them ideal for integrating heterogeneous devices across wide area networks. This real-time visibility of production data enables engineers and plant management to rapidly diagnose machine performance issues remotely, significantly reducing downtime. Instead of reacting to equipment failures, IIoT systems allow proactive maintenance. Engineers can remotely monitor machinery conditions, quickly identify trends that indicate wear or impending failure, and take preventive measures before actual breakdowns occur. This approach, known as predictive maintenance, leverages artificial intelligence and machine learning-driven analytics that continuously learn from historical performance data to predict the optimal time for maintenance interventions. To implement predictive maintenance successfully, controls engineers must integrate sophisticated AI-driven algorithms into data analytics platforms, either cloud-based or deployed locally at the network edge. Edge computing, in particular, is an important component of Industry 4.0 as it enables real-time data processing close to the machinery itself, minimizing latency and reducing bandwidth load on higher-level cloud systems. Engineers should also design systems that intelligently decide what data requires real-time transmission to the cloud and what data can be processed locally, balancing bandwidth usage and responsiveness. 9.1.3 Remote monitoring. Another crucial aspect of Industry 4.0 is remote monitoring and diagnostics capability. Controls engineers often incorporate secure remote access features into their automation system designs, allowing expert personnel or external support providers to monitor, diagnose, or update control systems without physically attending the site. Remote connectivity can significantly reduce downtime by enabling rapid troubleshooting, software updates, and configuration adjustments from any authorized location. To achieve this securely, engineers must adhere strictly to cybersecurity standards such as IEC 62443, implementing robust encryption, TLS, SSL, firewall protection, VPN connections, secure authentication, and clearly defined access roles and permissions. To realize the full potential of IIoT, controls engineers must also integrate control systems seamlessly with higher-level business systems like manufacturing execution systems, MES, and enterprise resource planning, ERP. Following standards such as ISA 95 ensures effective information exchange between control systems and enterprise-level software, enabling real-time production tracking, resource planning, inventory management, and business-level decision-making based on accurate production data. This integration provides greater transparency across production operations, allowing manufacturers to dynamically adjust production schedules, optimize resource allocation, and respond promptly to market demands or disruptions. 9.1.4 Digital Twins. Finally, Industry 4.0 encourages the use of digital twins, virtual replicas of physical machines or entire production lines that mirror the real-world system. Controls engineers can use digital twins to simulate, validate, and optimize machine performance, troubleshoot issues virtually before physical commissioning, and continuously evaluate potential system improvements. Digital twins integrate real-time data from sensors, PLCs, and analytics platforms, enabling engineers to predict how physical systems will respond to changes or upgrades without risking disruption to ongoing operations. In summary, Industry 4.0, driven by IIoT, real-time analytics, predictive maintenance, remote diagnostics, and cloud connectivity, fundamentally changes how automation systems are designed and operated. Controls engineers must embrace secure, interconnected, and data-driven architectures, aligning their designs to Industry 4.0 best practices and standards, ensuring their systems deliver lasting benefits such as reduced downtime, optimized performance, predictive insights, and superior integration with enterprise systems. 9.1.5 Connectivity in smart factories. Reliable connectivity forms the foundation of any modern smart factory, allowing machines, control systems, and software platforms to exchange critical operational data in real time. A successful Industry 4.0 implementation relies heavily on robust, deterministic, and secure industrial networking architectures, ensuring machines and automated systems can communicate reliably, securely, and seamlessly. 9.1.5.1 Profinet. Industrial Ethernet protocols form the core communication infrastructure within modern automation systems. Among the most widely implemented protocols is Profinet, an open standard widely utilized in Siemens automation systems. Profinet provides deterministic real-time control capabilities, critical for synchronized motion control, robotics, and high-speed PLC operations. It enables rapid data exchange cycles, typically in milliseconds or even microseconds for time-sensitive applications, and supports comprehensive device diagnostics, network redundancy, and seamless integration with functional safety protocols like ProfiSafe. 9.1.5.2 Ethernet IP. Another prominent protocol, widely used across many manufacturers, including Rockwell Automation, is Ethernet IP. This protocol leverages the Common Industrial Protocol CIP, facilitating interoperability and real-time communication between PLCs. I/O modules drive sensors and safety devices. Ethernet IP provides deterministic control through explicit and implicit messaging, allowing efficient real-time control, configuration, and diagnostics within multi-vendor automation environments. 9.1.5.3 OPC UA. Complementing these, protocols such as OPC Unified Architecture, OPC UA, enable standardized cross-platform communication, providing a flexible and scalable means of exchanging information between automation devices and higher-level systems, MES, ERP, cloud analytics. OPC UA offers robust security, built-in encryption, authentication, structured data modeling, and platform independence, making it ideal for cloud integration and IIoT applications. 9.1.5.4 Wireless. Beyond wired connectivity, wireless networks are increasingly employed within industrial environments, enabling mobility, remote monitoring, and flexible machine deployment. Wi-Fi standards, IEEE 802.11, and cellular technologies such as 4G/5G provide wireless connectivity suitable for applications like automated guided vehicles, AGVs, autonomous mobile robots, remote maintenance tools, and sensors placed in inaccessible or hazardous locations. For example, industrial Wi-Fi IEE 802.11 ABGNAC offers rapid deployment and flexible connectivity, though engineers must carefully manage interference, range, and reliability considerations due to potential signal attenuation and environmental challenges. Real-time deterministic requirements typically rely on wired Ethernet or specialist wireless protocols. The selection between wired and wireless often involves a trade-off between deterministic performance and mobility, demanding a thorough evaluation of application-specific latency and reliability requirements. 9.1.5.5 Cybersecurity. A key aspect of modern connectivity in smart factories is robust cybersecurity. Adherence to cybersecurity standards, especially IEC 62443, is essential for protecting industrial networks from cyber threats. Engineers must apply comprehensive security measures, including network segmentation, secure firewalls, and virtual private networks, VPNs, ensuring clear isolation between control networks and external networks. Segmentation significantly reduces the attack surface and limits the potential damage from cybersecurity incidents by containing them within isolated network zones. 9.1.5.6 Role-Based Access. Implementing role-based access control, RBAC, is also crucial for restricting system access to authorized personnel only. RBAC helps to prevent unauthorized actions by limiting operator and maintenance personnel to specific permissions based strictly on their role, ensuring that only trained and authorized personnel perform sensitive tasks or system adjustments. All interactions, particularly remote access sessions, should be logged in audit trails, ensuring traceability and accountability. Data integrity and confidentiality are fundamental, requiring end-to-end encryption for all communications. Protocols such as TLS Transport Layer Security and SSL Secure Sockets Layer provide secure communication channels, protecting sensitive process data against interception or manipulation, which is vital in highly regulated industries like pharmaceutical or chemical processing. Controls engineers designing modern industrial networks must also ensure that hardware and software components comply with cybersecurity standards such as IEC 62443. This standard provides a detailed framework for identifying vulnerabilities, establishing appropriate security levels, and implementing continuous monitoring and response strategies. Engineers must rigorously document network designs and test their security measures regularly to ensure ongoing compliance. Overall, connectivity in Industry 4.0 is not simply about physical networking, but requires a holistic approach encompassing deterministic communication protocols, robust cybersecurity strategies, and secure integration of wired and wireless technologies. Controls engineers must carefully consider protocol selection, network topology, security architectures, and integration requirements, enabling their automation systems to achieve reliable and secure operation, facilitating real-time data-driven decision-making, and laying the foundation for future scalability and technological advancement in smart factory environments. 9.2 Common Industry 4.0 Terms Explained. Industry 4.0 introduces a new set of key performance indicators, KPIs, and methodologies that drive operational improvements. This section explains the most commonly used terms in modern manufacturing and automation. 9.2.1 Overall Equipment Effectiveness, OEE. OEE measures how efficiently a machine or production line operates by combining three factors: availability, how often it runs without downtime; performance, how fast it operates compared to its maximum speed; and quality, how many parts produced are good versus defective. It is calculated as OEE equals availability times performance times quality. 9.2.2 Manufacturing Execution System. An MES is software that tracks factory production in real time, linking shop floor systems like PLCs and SCADA directly to business level software, helping to organize and optimize production schedules. 9.2.3 Enterprise Resource Planning, ERP.
ERP software manages broader company activities such as inventory, finances, ordering, and scheduling. MES connects to ERP to keep the factory aligned with overall business objectives.
9.2.4 Predictive Maintenance, PDM. Predictive maintenance, PDM, uses real-time sensors and advanced software analytics, including AI-driven machine learning models, to predict equipment failures before they occur. It involves analyzing vibration data to detect bearing wear or misalignment, thermal imaging to spot overheating components, and electrical analysis like motor current monitoring to anticipate mechanical or electrical faults. PDM moves maintenance away from scheduled or reactive methods toward a data-driven strategy, significantly reducing unplanned downtime, extending equipment lifespan, and cutting operational costs. 9.2.5 Time-Sensitive Networking, TSN. TSN is a set of IEEE Ethernet standards enabling deterministic low-latency communication on standard Ethernet networks, allowing real-time control signals and general data to coexist reliably. 9.2.6 Unified Namespace, UNS. Unified Namespace, UNS, is a centralized way of organizing and sharing industrial data, where every system, PLCs, SCADA, MES, ERP, sensors, publishes information into a common structured data model. Rather than separate point-to-point integrations, UNS creates a single real-time data source, allowing easy access and visibility for all connected devices and systems, simplifying integration and enabling Industry 4.0 applications. 9.3 Machine Learning and AI in Automation. Artificial intelligence, AI, and machine learning, ML, are rapidly transforming industrial automation, enabling machines and systems to go beyond the capabilities of traditional control logic. This shift provides factories with increased flexibility, adaptability, and intelligence. Controls engineers now have opportunities to integrate advanced AI-driven technologies into existing and new automation systems, significantly enhancing performance, safety, and efficiency. 9.3.1 Automated Root Cause Analysis and Fault Detection. AI-based root cause analysis is transforming how engineers manage machine failures and faults. Traditional fault-finding methods often rely on manual troubleshooting, operator experience, or time-consuming diagnostic procedures. With AI integration, control systems can automatically process and analyze historical and real-time data, quickly pinpointing underlying causes of production interruptions. For example, AI algorithms can correlate patterns of vibration, temperature fluctuations, current spikes, and subtle sensor anomalies to specific mechanical or electrical issues. The result is faster, more accurate fault diagnosis, and shorter downtime, as operators receive precise information on the root cause rather than broad or vague alarm messages. 9.3.2 Dynamic Process Optimization using AI-driven feedback loops. Traditional control loops, such as PID controllers, are effective but often struggle when processes change rapidly or involve complex interactions. AI-driven feedback loops provide an advanced, adaptive alternative. Using machine learning algorithms trained on historical and real-time production data, the control system can dynamically optimize parameters such as motor speeds, valve positions, temperature settings, or flow rates based on live conditions. For instance, an AI model integrated into a PLC can adjust dosing rates dynamically to achieve precise chemical blending, even as raw material properties vary, improving product quality and process efficiency. This approach moves beyond static, pre-tuned parameters, providing responsive, self-optimizing systems that adjust to process variability automatically. 9.3.3 Autonomous Robots and Automated Guided Vehicles, AGVs. In modern automated facilities, autonomous robots and AGVs have become commonplace. AI enhances these robotic systems by allowing sophisticated motion planning, obstacle avoidance, and route optimization. Traditional AGV systems typically rely on predetermined paths and rigid navigation routines. With AI, autonomous robots and AGVs can interpret sensor data from LiDAR, vision systems, and other environment sensing technologies, dynamically recalculating paths in real time to safely avoid collisions with operators, machinery, or other AGVs. This significantly reduces downtime and potential safety hazards, while improving throughput and operational flexibility. Controls engineers must ensure robust communication between these AI systems, the central PLC or MES, and enterprise-level planning software to maintain coordinated production flow. 9.3.4 Vision Systems enhanced with machine learning. AI has greatly advanced the capabilities of machine vision systems for inspection and quality control. Conventional machine vision relies on rigid, rule-based image processing that struggles with variability in lighting, positioning, or product appearance. AI-enhanced vision systems utilize neural networks and machine learning models trained on thousands of product images to recognize defects, measure quality parameters accurately, and perform automated sorting with high reliability. Controls engineers integrating AI-driven vision inspection need to carefully design systems to collect high-quality training data, implement robust communication with PLCs for real-time sorting decisions, and manage model updates and retraining to adapt to production changes over time. And 9.3.5 Predictive Maintenance and Condition Monitoring. AI-driven predictive maintenance continues to evolve as a powerful tool for preemptively identifying equipment faults. Machine learning models analyze large historical datasets gathered from sensors, such as motor vibration profiles, acoustic signatures, temperature patterns, and power consumption to identify early signs of failure. Controls engineers must integrate sensors and PLC data logging capabilities to feed accurate, high-quality data into these predictive models. Real-time predictions can then be integrated into SCADA or HMI displays, triggering alerts that direct maintenance teams to act before costly breakdowns occur. 9.3.6 Digital twins and simulation-based AI control. Digital twins are advanced virtual models of physical processes or machines that use AI-driven analytics to simulate and optimize real-world conditions in real time. Controls engineers designing digital twins must create secure real-time data streams from PLC systems, sensors, and actuators to feed accurate information into the virtual model. AI algorithms then analyze this data to optimize parameters such as cycle times, energy consumption, and predictive maintenance schedules. Digital twins also allow virtual commissioning, reducing physical testing time by enabling controls engineers to simulate and debug PLC logic virtually, minimizing project risks and implementation time. 9.3.7 AI Summary. Artificial intelligence is rapidly becoming a core element of modern industrial automation. Controls engineers who successfully integrate AI-driven tools such as root cause analysis, dynamic optimization, autonomous vehicles, advanced vision systems, predictive maintenance, and digital twins gain a significant competitive advantage through increased uptime, improved quality, safer operations, and reduced maintenance costs. Successfully deploying these technologies requires thoughtful system architecture design, careful sensor and hardware integration, robust network communication, and an understanding of machine learning principles. By embracing these advanced methods, controls engineers position their automation systems and processes for future-ready, flexible, and highly intelligent manufacturing.
9.4 IIoT Summary.
Industry 4.0 is redefining automation with IIoT, AI, machine learning, and cloud computing enabling real-time optimization of industrial processes. Controls engineers must integrate these technologies into factory automation designs to ensure future-proof, scalable, and efficient industrial systems. 10 Practical engineering and maintenance. And industrial automation systems are not just designed and installed, they must be maintained, optimized, and adapted over time to ensure continued reliability, efficiency, and compliance with evolving standards. Effective engineering extends beyond initial commissioning, requiring structured maintenance strategies, systematic troubleshooting, and forward-thinking lifecycle management. This section explores key maintenance principles, including predictive and preventive maintenance techniques, fault diagnosis methodologies, and strategies for minimizing unplanned downtime. It also covers startup and commissioning best practices, ensuring that systems are properly tested, validated, and optimized before going into full production. As automation technology advances, engineers must also navigate legacy system upgrades and modernization, balancing the risks of obsolescence with the need for cost-effective retrofits. By understanding the challenges of integrating new technologies with existing infrastructure, engineers can develop upgrade plans that enhance performance while maintaining operational continuity. By applying structured maintenance approaches, robust troubleshooting techniques, and strategic upgrade planning, controls engineers can extend the lifespan of industrial systems, improve plant reliability, and support long-term operational success. 10.1 Maintenance and Troubleshooting. 10.1.1 Electrical and Mechanical Troubleshooting Techniques. Effective troubleshooting combines both electrical and mechanical diagnostic methods. On the electrical side, troubleshooting typically starts with a visual inspection of panels and components for signs of overheating, loose terminals, or damaged cables. A systematic approach is then followed using electrical drawings and I/O lists. Test equipment such as multimeters, insulation resistance testers, and oscilloscopes are used to check for short circuits, open circuits, incorrect voltages, and faulty signals. PLC diagnostics, including status LEDs, fault codes, and system logs, are essential tools to isolate faults within the control system. For mechanical systems, common techniques include physical inspection for misaligned or worn components, checking tension in belts and chains, and verifying the integrity of bearings and shafts. Vibration analysis is often used to detect early signs of mechanical failure, such as bearing wear or unbalanced loads. Pneumatic and hydraulic systems require pressure checks and leak detection to ensure actuators are functioning correctly.
10.1.2 Preventive and Predictive Maintenance, TPM RCM.
Preventive maintenance focuses on scheduled inspections and part replacements to prevent failures before they occur. This includes routine lubrication, cleaning, tightening of electrical connections, and periodic replacement of components subject to wear, such as seals and filters. Total productive maintenance, TPM, encourages operator involvement in basic maintenance tasks, such as inspection and minor adjustments, helping to identify potential issues early. Predictive maintenance uses real-time condition monitoring to predict failures before they occur. Vibration sensors can detect issues with motors and gearboxes, thermal cameras identify overheating electrical components, and AI-based systems analyze data trends to foresee problems. This approach reduces unnecessary maintenance while avoiding unexpected failures. Reliability-centered maintenance, RCM, combines these methods by assessing the criticality of equipment and determining the most appropriate maintenance strategy based on risk and consequence of failure. 10.1.3 Common failures and how to address them. In industrial automation, many failures share common causes. Sensor failures often arise from contamination, physical damage, or wiring faults. These can typically be addressed by cleaning, inspecting connections, and replacing damaged sensors. Drives and VFDs may trip due to overcurrent, overheating, or communication issues, which should prompt checks on motor load, drive cooling, and network integrity. PLC input and output faults are frequently caused by blown fuses, wiring issues, or failed I/O cards. Diagnosing these faults involves checking wiring continuity, verifying terminal connections, and using spare I/O channels for testing. Motor failures can result from mechanical overload, bearing failures, or electrical insulation breakdown. These are identified through thermal testing, vibration monitoring, and insulation resistance checks. Pneumatic failures often involve actuator leaks or worn seals, requiring inspection, pressure tests, and component replacement. Network communication failures typically stem from electromagnetic interference, damaged cables, or configuration errors, and require a thorough examination of cabling and network devices. 10.2 Startup and Commissioning. 10.2.1 Planning and Documentation. The success of system commissioning and initial startup is fundamentally dependent upon meticulous planning, detailed documentation, and a structured verification process. Planning and documentation underpin every stage of commissioning, from initial power-up tests to full operational validation, and are essential for safety compliance, efficient troubleshooting, and system reliability. Comprehensive commissioning begins long before the equipment is powered on. Controls engineers must prepare thorough planning documents, ensuring all stakeholders clearly understand system requirements, expected performance criteria, and safety considerations. Essential planning documentation typically includes accurate and detailed functional specifications, safety requirement specifications, SRS, IO listings, and process control narratives. In the UK and EU, standards such as EN 60204-1, Electrical Equipment of Machines, and the Machinery Directive 2006/42/EC mandate clear, precise documentation to demonstrate regulatory compliance, safe design principles, and adherence to CE or UKCA marking requirements. Electrical and control schematics must be accurate, detailed, and fully compliant with relevant standards. UK control engineers commonly follow EN 60204-1 for machinery safety, BS 7671, IET wiring regulations, for electrical installations, and IEC 61439 for panel construction guidelines. Detailed drawings should clearly indicate component layout, cable routing, fuse ratings, circuit breaker ratings, wiring sizes, color coding, and terminal numbering to aid electricians and panel builders in accurate assembly. Manufacturers' manuals for key components, such as PLCs, drives, or safety devices, must be thoroughly reviewed during planning, confirming critical specifications like environmental operating conditions, heat dissipation requirements, clearances for cooling, and recommended maintenance intervals. Beyond functional requirements, engineers should include clearly structured commissioning and testing plans detailing step-by-step procedures to bring equipment online. This commissioning plan specifies tests to verify correct hardware installation, functional logic verification, safety circuit operation, SIL or PL validation, network communication integrity, and system integration with supervisory control and enterprise-level software, MES and ERP. Each commissioning test should have clearly defined acceptance criteria and expected outcomes, enabling systematic tracking of progress and early detection of problems or deviations. 10th point 2.2 Documentation requirements for commissioning. The role of complete and accurate documentation cannot be overstated. Detailed commissioning documentation ensures that every stakeholder, from electricians and panel builders to plant operators and maintenance personnel, fully understands the system's function, safety constraints, and operating procedures. Comprehensive documentation reduces the risk of mistakes, improves troubleshooting efficiency, and is essential for ongoing regulatory compliance. Critical documentation to prepare includes detailed functional descriptions, electrical schematics, bill of materials BOM, cable schedules, panel layouts, wiring diagrams, I/O lists, and detailed commissioning checklists. Engineers must clearly record every step taken during testing, including test methods, results, any required modifications, and retests performed after corrections. Test plans must specify clear acceptance criteria aligned with the original functional specification and regulatory requirements, ensuring that the system meets intended operational standards. The structured documentation must also capture and clearly reference all safety-related tests and verification procedures. Safety validation should demonstrate compliance with ISO 13849-1 or IEC 62061 standards, including recorded proof of achieving required performance levels or safety integrity levels. Explicit verification records of emergency stop functionality, interlock operation, safe motion tests, e.g., safe torque off or safe limited speed, and fault response scenarios should be meticulously documented. Engineers should also produce user manuals and operational guides that provide clear, straightforward instructions for operators. Manuals must define normal operating procedures, routine maintenance instructions, troubleshooting guides, and clearly labeled diagrams for operator reference. The documentation should include explicit references to the actual components used, including clear guidance from component manufacturers regarding any required installation considerations, such as minimum clearance for heat dissipation, appropriate torque for terminal connections, and environmental limitations, temperature, humidity, vibration. Additionally, comprehensive commissioning documentation typically includes factory acceptance test, FAT, and site acceptance test, SAT reports. FAT documentation confirms that the system meets functional criteria at the manufacturer's or integrator's site prior to shipment, while SAT, site acceptance test, documentation confirms that equipment performs correctly once installed on site, meeting all user and functional requirements. Finally, controls engineers should produce detailed training documentation and operational manuals tailored for operators and maintenance personnel. These must clearly outline correct machine operation, startup and shutdown procedures, troubleshooting techniques, and routine maintenance schedules to maintain reliable long-term performance and safety. 10th point 2.3 Testing and debugging control systems. Comprehensive testing and debugging are vital to ensure that automation systems operate safely, reliably, and as designed. This process begins after assembly and continues systematically until full operational performance is verified. Controls engineers oversee this phase, applying rigorous procedures to validate every aspect of the control architecture, hardware components, software logic, safety measures, and communication networks. Testing typically starts with detailed verification of electrical installations. All wiring and connections should first be checked against electrical schematics and wiring diagrams for accuracy, continuity, and proper termination. Initial inspections must verify that correct cable sizing and ratings have been applied according to UK and EU standards, e.g. EN 60204-1, IEC 61439. Checks include ensuring terminal connections are secure and correctly torqued, cables are properly earthed, shielding is effectively implemented to reduce electromagnetic interference, EMI, and clear separation of power and control wiring is maintained. PLC-based testing usually follows a structured process. Individual control routines are first tested independently, then combined progressively into more extensive sequences. Input and output I/O testing involves methodically activating and verifying each sensor, actuator, and connected device, ensuring the PLC accurately reflects real-world conditions. For instance, digital inputs must confirm accurate switching under correct voltages, and analog sensors must undergo signal scaling checks to confirm they provide accurate, stable values. Actuators such as valves and contactors are systematically energized and monitored, confirming both the actuation logic and feedback mechanisms function as expected. Software logic tests typically start at a modular level, verifying each function block, safety routine, or control algorithm separately before integrating them into complete sequences. For example, individual PID loops controlling variables such as pressure or flow are initially tuned and validated in isolation. Once individual routines pass initial tests, controls engineers move to integrated system tests, progressively combining software modules and checking interactions between devices and sequences. For example, a filling station controlled by PLC logic might first verify the tank level control function block separately, then test valve control logic individually, and finally combine both functions in an integrated test to confirm correct coordinated operation. Safety system verification is particularly critical. Functional safety systems governed by ISO 13849-1 or IEC 62061 require validation under realistic fault conditions to confirm that safety functions respond correctly to hazardous scenarios. Emergency stops must reliably remove hazardous energy, interlocks should correctly detect and respond to unauthorized access, and safety-rated sensors, such as light curtains or area scanners, must immediately halt hazardous machine motion upon intrusion. Engineers typically introduce intentional faults or simulated conditions, such as sensor disconnections or actuator failures, to confirm safety logic, responds correctly, promptly initiating safe shutdowns or stopping motion. Motion control elements, including conveyors, robots, or servo-driven mechanisms, require controlled and careful commissioning tests. Systems are first tested at reduced speeds and controlled environments to validate fundamental functions like homing, jogging, or basic positioning accuracy. Once these are confirmed, engineers progressively move to full speed, realistic operational conditions to verify acceleration, deceleration, load handling capability, collision avoidance logic, and emergency stopping performance. Engineers should ensure all motion parameters, acceleration, deceleration, jerk limits, are carefully tuned to minimize mechanical stress, and positioning accuracy meets design specifications under all load conditions. Network and communication checks confirm that all devices communicate effectively via selected industrial protocols: Ethernet IP, Profinet, OPCUA. Engineers validate response times, communication integrity, data throughput, and diagnostic messaging. In networked systems with distributed I/O or remote equipment, tests ensure robust detection and handling of network disruptions or failures. Network redundancy mechanisms, ring redundancy, redundant paths, must be tested to confirm seamless failover in the event of cable breaks or device failures. System debugging requires methodical recording and analysis of unexpected behavior. Engineers utilize PLC diagnostics, monitoring scan times, processor loads, and logic execution speeds, identifying inefficiencies or bottlenecks that require optimization. Tools like oscilloscopes, network analyzers, and data loggers may be employed to investigate electrical or communication anomalies in depth. HMIs and SCADA systems should be simultaneously validated, ensuring alarms and diagnostics generated by the PLC appear correctly, clearly, and immediately to operators. Finally, thorough documentation of all tests performed, including clearly recorded results, acceptance criteria, any issues identified, and corrective actions taken, is mandatory. A structured test documentation approach supports future maintenance,
simplifies ongoing troubleshooting, and ensures traceability for compliance audits.
10th point, 2.4 System Validation and FAT-SAT. System validation involves rigorously confirming that a control system meets all defined functional, safety, and performance requirements. 2 formal stages: factory acceptance testing, FAT, and site acceptance testing, SAT, ensure the system operates reliably, safely, and fully in accordance with specified requirements. Factory acceptance testing, FAT, is carried out at the manufacturer's or system integrator's premises before shipping equipment to the end user's site. During FAT, engineers systematically verify that the system performs precisely according to the agreed upon functional specifications, including detailed testing of PLC logic, HMI screens, alarms, diagnostics, network communications, and safety functions. Tests should replicate realistic operational conditions wherever possible, simulating input-output scenarios, fault conditions, and emergency responses. For example, controls engineers may simulate sensor faults to confirm that diagnostic alarms trigger correctly, or conduct controlled simulations of safety device activations, such as e-stop or guard interlocks, to verify adherence to required safety standards, e.g., ISO 13849 for performance levels or IEC 62061 for SIL. Once the FAT is successfully completed, a detailed test report is generated, documenting each test conducted, outcomes, and any adjustments made to ensure full compliance. This documentation should clearly identify software revisions, component configurations, calibration details, and settings used during testing. Documentation from FAT includes a comprehensive record of acceptance tests performed, signed-off test protocols by engineers, and formal confirmation of adherence to relevant regulatory standards, particularly those required in the UK and EU, such as Machinery Directive 2006/42/EC compliance, EN 60204-1 for electrical safety, ISO 13849-1, or IEC 62061 for functional safety validation. Following successful factory acceptance testing, equipment is shipped to the production site, where site acceptance testing, SAT, is conducted. The SAT confirms not only that equipment survived transport without damage, but also that it integrates seamlessly into the wider manufacturing environment and performs as expected under real, site-specific conditions. During SAT, controls engineers methodically revalidate all critical functions tested during the FAT, plus additional integrated system checks that can only be performed on site, such as confirming correct integration with existing site infrastructure, upstream and downstream processes, and on-site utility supplies, compressed air, electrical power, hydraulics, cooling water. Engineers must thoroughly test safety devices and circuits under realistic scenarios, including verifying emergency stop functionality, ensuring interlocks activate appropriately during equipment interactions, and validating safety network communication protocols, e.g., ProfiSafe. The SAT phase typically involves close collaboration with end-user operational and maintenance teams, providing an opportunity to confirm correct system functionality, fine-tune operational parameters, and ensure plant-specific requirements are fully satisfied. Controls engineers should actively involve end-user personnel during SAT to facilitate knowledge transfer, ensuring operators and maintenance technicians are familiar with the system and its controls, alarms, diagnostic functions, and troubleshooting procedures. Like the FAT, SAT concludes with a formalized acceptance procedure documented thoroughly in a detailed SAT report. This document confirms final system configurations, captures all adjustments or modifications made on site, lists unresolved issues with clear plans for resolution, and includes formal sign-off by the customer acknowledging acceptance and readiness for operational use. SAT documentation also explicitly references the safety validation results against standards such as ISO 13849 performance levels or IEC 62061 SIL classifications, providing essential evidence of regulatory compliance required by health and safety authorities. Effective validation through structured FAT and SAT ensures control systems perform reliably from initial deployment onwards with minimal unexpected downtime or performance issues. For controls engineers, these testing phases are critical opportunities to proactively identify and correct problems in a controlled environment, ensuring robust and reliable system performance, regulatory compliance, and operator confidence in production. 10.3 Legacy system upgrades and modernization. Legacy automation systems pose considerable risks due to obsolescence, including unavailable spare parts, discontinued software support, and non-compliance with current safety standards. Managing these risks begins with accurately identifying outdated components and understanding the potential impact of their failure. An up-to-date asset register containing detailed information on all existing control hardware, software versions, firmware revisions, and support status is essential for efficient obsolescence management. Engineers must evaluate the urgency of upgrading each asset based on the probability of failure and the resulting operational impact, aligning this prioritization with available budgets and operational objectives. When planning a migration to modern equipment, it's crucial to clearly define the system's upgrade path. For simpler or relatively recent legacy systems, a direct replacement strategy may be sufficient. This often involves replacing the legacy PLC or HMI with newer models offered by the same vendor, enabling minimal disruption and straightforward code migration. Direct replacements can usually retain existing wiring, I/O modules and sensors, reducing implementation time and lowering risk. Phased upgrades are particularly beneficial when downtime must be minimized. For instance, engineers might first replace outdated human-machine interfaces, HMIs, with modern touchscreen devices, preserving the existing programmable logic controllers, PLCs, temporarily. In subsequent phases, the PLC and I/O modules can be upgraded. This phased approach allows incremental validation at each step, significantly reducing downtime risk and spreading capital expenditure over a manageable period. In cases where systems are extensively outdated, unsafe, or cannot meet current standards, a complete redesign is advised. This scenario typically involves re-evaluating system architecture, communication networks, and safety measures from the ground up. Comprehensive redesigns must include modern hardware choices compliant with current standards such as EN 60204-1, safety of machinery, electrical equipment, ISO 13849-1, functional safety, and IEC 62061, safety integrity level. This redesign also presents an opportunity to incorporate contemporary technologies, including advanced data analytics, wireless communication, and enhanced cybersecurity measures aligned with IEC 62443. Risk management is a critical aspect of legacy system modernization. Retrofit projects commonly uncover hidden issues such as undocumented modifications, incorrect or faulty wiring, and compatibility problems with newer devices. Controls engineers must develop detailed scopes of work with clearly documented boundaries, specifying precisely which equipment remains and which is replaced. The budget planning stage should anticipate and allocate funds for unforeseen issues, such as additional wiring requirements, I/O expansion, or structural panel modifications. System testing during migration is paramount and should encompass both the replaced components and existing equipment. Comprehensive verification plans, including factory acceptance tests, FAT, and site acceptance tests, SAT, must ensure that each upgrade phase performs correctly within the integrated system environment. Validation of safety functionality is essential, ensuring the modern system meets all required performance levels P, L, or safety integrity levels SIL. Tests should systematically validate functional logic, alarm management, network communication, and operator interface effectiveness. Finally, rigorous documentation updates and clear communication with operators and maintenance personnel are essential. Controls engineers should revise electrical schematics, wiring diagrams, user manuals, and training materials to reflect system changes accurately. Training sessions must ensure operators and maintenance teams fully understand new features, controls, alarms, and diagnostic methods, facilitating a smooth transition from legacy systems to modern, efficient, and compliant automation solutions. 10.4 Practical engineering summary. Practical engineering and maintenance underpin the reliability and longevity of industrial automation systems. Controls engineers are essential not only in initial system design, but throughout the system's lifecycle, ensuring sustained performance and compliance. Effective maintenance involves systematic troubleshooting, root cause analysis, and predictive strategies to proactively identify and resolve potential failures. Successful system startup and commissioning require meticulous planning, comprehensive documentation, rigorous testing, and thorough validation to ensure smooth, safe operation from day one. Managing legacy systems demands strategic approaches, balancing direct replacements, phased upgrades, or complete redesigns to address obsolescence while controlling risks and costs. By combining structured methodologies, detailed documentation, proactive maintenance, and careful upgrade planning, controls engineers significantly enhance system reliability, safety compliance, and operational efficiency, minimizing downtime and extending system life.
11. Future-proofing, security, and human factors. As industrial automation evolves, controls engineers must design systems that are not only functional today, but also adaptable, secure, and efficient for years to come. The rapid integration of cloud computing, IIoT, AI, and data-driven decision-making is transforming the automation landscape. But these advancements also introduce new challenges. Systems must be future-proofed against obsolescence, hardened against cyber threats, and engineered with human operators in mind to ensure usability and long-term reliability. This section explores three critical areas shaping the future of industrial automation. First, cybersecurity is a growing concern as connected systems become targets for malicious attacks, requiring controls engineers to implement robust security frameworks, network segmentation, and access controls in compliance with IEC 62443. Second, human factors play a crucial role in automation effectiveness. Intuitive HMIs, ergonomic workstations, and well-structured alarm management can significantly improve operator performance and reduce error rates. Finally, sustainability and energy efficiency are becoming industry imperatives, driving the need for green automation practices, intelligent energy monitoring, and waste reduction strategies that align with global environmental goals.
By designing secure, user-friendly, and resource-efficient control systems, engineers can create resilient and adaptable automation solutions that stand the test of time. The key to future-proofing is not just anticipating change, but building systems that can evolve with it. 11.1 Cybersecurity for control systems. 11.1.1 Threats to industrial systems. As industrial automation becomes more digitally interconnected, control systems that were once isolated now face significant cybersecurity challenges. The rise of Industry 4.0 IoT and cloud integration increases exposure to both internal and external cyber threats, making robust cybersecurity essential to maintaining safe and reliable production. One of the most severe threats to industrial systems is ransomware and malware attacks, where malicious software infects critical PLCs, SCADA systems, or operator workstations, potentially causing prolonged downtime, data loss, and expensive recovery processes. Ransomware attackers often encrypt key system files, locking engineers and operators out of critical infrastructure until ransom demands are met. Network intrusions present another serious threat, with unauthorized access potentially originating externally or internally from compromised or negligent users. Attackers can exploit weak authentication methods, outdated software, or unpatched security vulnerabilities, gaining access to sensitive operational networks. Once inside, attackers can manipulate control logic, steal confidential operational data, or cause significant physical damage by altering control signals or disabling protective systems. Remote access, increasingly common for vendor support and system monitoring, introduces vulnerabilities if improperly secured. Third-party connections that lack robust authentication protocols, secure communication channels, or strict access control policies can serve as entry points for cyber criminals. Attackers exploiting these vulnerabilities can gain control of critical industrial assets, disrupt production schedules, or introduce malicious logic into system programming. Phishing and social engineering attacks pose a significant risk, particularly targeting operational technology, OT personnel, who may have less cybersecurity training compared to IT staff. These attacks typically involve deceiving personnel into revealing sensitive login credentials, downloading malicious software, or unwittingly allowing attackers direct access to industrial systems. Human error, amplified by insufficient security awareness and training, significantly increases susceptibility to these threats. Finally, manipulation of control signals is an alarming cyber threat specific to industrial environments. Attackers may deliberately change set points, suppress critical alarms, or alter the communication of safety systems, leading to unsafe and potentially catastrophic operational conditions. Such manipulation can remain hidden until a major failure or safety incident occurs, underscoring the critical need for robust, secure system design. Given the severity and evolving nature of these threats, controls engineers must prioritize embedding robust cybersecurity measures into every phase of system design and lifecycle management, from initial architecture planning to ongoing maintenance and operational vigilance. 11.1.2 Basic Security Measures IEC 62443. The IEC 62443 standards provide a comprehensive, internationally recognized framework specifically designed for securing industrial control and automation systems. Controls engineers can apply these principles throughout system design, implementation, and operation to significantly reduce vulnerability to cyber threats. The principle of defense in depth is fundamental. This strategy involves layering multiple independent security measures at various levels of the control architecture, ensuring that if one security mechanism fails, others remain effective. Defense in depth covers physical access restrictions, network security, host-level protections, application layer safeguards, and robust procedures and policies. By embedding security at every layer, from the corporate enterprise network down to individual PLCs and sensors, the risk of a single point of failure compromising the entire system is minimized. Network segmentation is crucial in clearly defining and isolating network traffic, especially between information technology, or IT, and operational technology, and OT systems. Implementing firewalls, virtual local area networks, VLANs, and demilitarized zones, DMZs, restricts network traffic to authorized paths, significantly limiting the potential impact of any intrusion. Network segmentation helps prevent lateral movement of attackers who have gained initial access, reducing exposure of critical industrial components. Clearly documented network diagrams should define communication rules and permitted data exchanges, facilitating easier monitoring and management of network traffic. Role-based access control, RBAC, restricts user privileges strictly to the tasks required by their roles. It ensures users receive only necessary permissions, preventing unauthorized access or modifications to critical systems and sensitive data. RBAC is complemented by strong user authentication methods, including secure passwords, multi-factor authentication, MFA, and timely revocation of access rights when roles or personnel change. Regular audits of user privileges are recommended to confirm compliance with access policies. Secure device configuration requires diligent attention to manufacturer-provided security guidelines. Default passwords on devices like PLCs, HMIs, and network switches must always be replaced with strong, unique passwords. Disabling unused ports, communication protocols, or services prevents unnecessary vulnerabilities. Firmware and software should be updated regularly according to the manufacturer's security advisories, applying patches promptly to protect against known vulnerabilities and exploits. System hardening includes proactive measures such as disabling unnecessary communication protocols, services, and ports on control hardware and network devices, significantly reducing potential entry points. Hardening also involves physically restricting access to critical automation hardware to prevent unauthorized manipulation or sabotage. Access controls and surveillance systems, such as card readers and CCTV cameras, should protect control rooms, data centers, and network cabinets to limit physical security breaches. Finally, effective monitoring and logging of system activity and network communications are essential for detecting and responding to potential security threats promptly. Real-time monitoring tools, intrusion detection systems, IDS, and log management solutions should be deployed to continuously assess traffic for abnormal patterns or indicators of compromise. Logs must be securely stored and regularly reviewed, supporting swift incident response and forensic investigations in case of cybersecurity incidents. By systematically applying these security measures according to IEC 62443, controls engineers can create resilient industrial automation systems capable of securely handling modern operational demands while effectively mitigating cybersecurity risks. 11.1.3 Secure remote access and maintenance. Remote access to industrial control systems, ICS, has become commonplace for enabling efficient diagnostics, troubleshooting, vendor support, and system updates. While highly beneficial, remote connectivity introduces significant cybersecurity risks if it is not carefully controlled and secured. Controls engineers must ensure that all remote access methods follow stringent security practices to maintain system integrity and prevent unauthorized intrusion.
A fundamental step for securing remote access is the use of virtual private networks, VPNs. A VPN creates an encrypted tunnel over public networks, ensuring data exchange between remote users and ICS components remains confidential and protected from interception. VPN connections must use strong encryption standards, such as IPsec or SSL/TLS, and robust protocols to maintain secure channels, preventing attackers from intercepting sensitive data or injecting malicious commands. Multi-factor authentication, MFA, significantly enhances remote access security by requiring users to verify their identity using multiple distinct verification methods, typically something the user knows, password, something they have, security token or mobile device, or something they are, biometric identification. MFA mitigates the risks posed by compromised passwords, reducing the likelihood of unauthorized remote access, even if login credentials are stolen.
Time-limited and monitored access sessions further improve security by restricting remote connection availability strictly to times when support activities are necessary. Controls engineers should configure remote access systems to enforce strict session durations and automatic session termination after periods of inactivity. This approach limits exposure to potential unauthorized access, especially when support or maintenance tasks are complete. Real-time monitoring of remote sessions ensures immediate detection and response to any unusual or suspicious activities. Implementing a jump server or gateway provides a controlled, centralized entry point for all remote access requests. Jump servers typically reside within a secure network segment, such as a DMZ, separate from the primary ICS network. Users connect first to the jump server through VPN and authentication, and from there securely access target devices. This method eliminates direct external connections to critical ICS components, significantly reducing the attack surface. Jump servers also allow IT or security personnel to closely monitor, control, and record each remote session, enabling tighter security and accountability.
Maintaining detailed audit trails and activity logs is crucial. Comprehensive logging of all remote access events, including user identification, access duration, system interactions, configuration changes, and executed commands, provides invaluable records for security analysis, troubleshooting, and compliance audits. Engineers and security teams should periodically review these logs for anomalies or indicators of malicious activities, facilitating rapid response to potential breaches.
Finally, remote access must be governed by comprehensive security policies and supported by ongoing user training. Policies should define clear roles, responsibilities, allowed activities, and prohibited behaviors. Training ensures that users understand risks, comply with best practices, and promptly report any security incidents or suspicious activities. Vendors and third parties granted remote access should be held to the same stringent security standards as internal personnel, including regular reviews of their access rights and compliance. By rigorously applying these secure remote access practices, controls engineers can leverage the productivity benefits of remote support while significantly reducing cybersecurity risks to critical industrial automation systems. 11.2 Human Factors in Automation. 11.2.1 Designing for Usability and Safety. Human factors are critical to the success of industrial automation systems. They directly influence safety, productivity, operator performance, and error prevention. A well-designed system anticipates human interaction under both routine and emergency conditions, guiding operators intuitively, minimizing confusion, and significantly reducing the likelihood of mistakes or unsafe actions. One fundamental design principle is creating clear and consistent operator interfaces. Following recognized guidelines such as ISA 101, Human-Machine Interface Design Standard, ensures that HMIs and SCADA screens present information logically and consistently. Screens should have intuitive navigation, standardized icons and symbols, clear text labels, and well-organized layouts. Critical information, such as alarms, operational states, and emergency indicators, must always be prominently displayed, easily identifiable, and readable under varied lighting and environmental conditions. The strategic use of colors and visual hierarchies can quickly alert operators to critical issues without overwhelming them with information, facilitating rapid and correct responses during operational or emergency situations. Controls engineers must design logical machine sequences that align closely with operator expectations and mental models. Clearly structured sequences with obvious transitions and explicit visual or audible feedback at each step significantly improve the operator's understanding of system behavior. Operators should be able to easily track a process step by step, quickly identify deviations, and intuitively understand corrective actions. Machine sequences designed with human cognition in mind help prevent inadvertent operator errors, reduce the cognitive load during complex processes, and ensure smoother transitions between operational states. The careful placement and design of emergency stops, E-stops, is vital to rapid and effective responses during emergencies. E-stops must be highly visible, consistently colored, typically red with yellow backgrounds, prominently located, and physically accessible from all operator positions. Compliance with EN ISO 13850, Safety of Machinery Emergency Stop Function, ensures that pressing an E-stop reliably halts hazardous machine functions immediately and safely. Controls engineers must avoid placing emergency stops in locations that could confuse operators or inadvertently cause activation or delays in critical emergency situations. Effective automation design minimizes unnecessary operator interventions to reduce the likelihood of human errors. This can be achieved through intelligent machine design, automated routines for repetitive tasks, and clearly defined decision support tools embedded within operator interfaces. Minimizing manual tasks reduces operator fatigue, lowers stress levels, and limits opportunities for inadvertent errors, resulting in higher productivity and safer operations. Automation should handle routine and repetitive operations, freeing operators to focus on monitoring, diagnostics, and decision-making where human judgment is essential. Implementing fail-safe defaults and meaningful error messages is another crucial human factor consideration. In the event of sensor failures, communication issues, or unexpected machine states, control systems should automatically enter safe states or shut down hazardous processes to prevent harm to operators or equipment. Clearly articulated error messages and alarms should explicitly state the nature of the issue, its exact location, potential impacts, and immediate actions required from the operator. Avoiding vague messages reduces confusion, speeds up corrective actions, and enables operators to manage situations confidently. Incorporating comprehensive operator training and ensuring good system documentation complements these design efforts. Training helps operators understand system behavior thoroughly, recognize abnormal conditions quickly, and respond appropriately in emergencies. Good documentation supports operators in troubleshooting and reinforces correct operational procedures. By integrating these human-centered design considerations, controls engineers create automation systems that not only enhance productivity, but also substantially improve operational safety, reduce downtime, and promote user confidence. 11th point 2.2 Ergonomics and operator interface. Ergonomic design is crucial in industrial automation, significantly improving operator comfort, performance, safety, and productivity. Controls engineers must carefully consider how physical and visual interactions with machinery influence operator effectiveness, accuracy, and long-term health. The physical placement of operator stations and human-machine interfaces, HMIs, is critical. Operator panels, touch screens, and control elements should be positioned thoughtfully, avoiding positions that require excessive reaching, stretching, twisting, or bending. Controls engineers should design stations within comfortable reach envelopes, ideally following guidelines from standards such as ENISO 14738, which specify recommended ergonomic reach distances. Components frequently used by operators, such as emergency stops, start-stop buttons, and common adjustments, must be easily reachable from the operator's normal standing or seated position without requiring awkward movements. Designing adjustable operator stations is recommended, allowing users of different heights and physical abilities to comfortably access control elements and clearly view information screens. Adjustable panels or screens, mounted on articulated arms or height-adjustable supports, enable easy repositioning. This flexibility accommodates multiple users, and reduces musculoskeletal strain from repetitive or uncomfortable movements, preventing fatigue and injury in long-term use. Screen readability is another important ergonomic factor. HMIs and control displays must remain clearly visible and legible under varying ambient lighting conditions typically found in industrial environments. Using appropriate font sizes, high contrast color schemes, such as white text on dark backgrounds or vice versa, and avoiding unnecessary visual clutter significantly improves readability and reduces operator eye strain. Anti-glare or matte screens are also advisable in brightly lit environments or outdoor settings, ensuring that operators can accurately interpret critical information at a glance. Alarms and notifications must be designed thoughtfully to avoid sensory overload while ensuring they are unmistakable and actionable. Controls engineers should implement alarms using a carefully balanced combination of visual and audible signals. Audible alarms should be loud and distinctive enough to catch operator attention in noisy industrial settings, but not excessively harsh, which could cause unnecessary stress or fatigue over extended periods. Visual alarms should clearly indicate the severity and nature of the issue using universally understood color codes, such as red for critical faults and amber for warnings, helping operators quickly prioritize and respond to events. Finally, ergonomic design involves simplifying operator workflows by structuring control interfaces logically and intuitively. Controls engineers should design interface screens and operating procedures that clearly guide operators step by step through machine operations, adjustments, and troubleshooting tasks. Interfaces should minimize complexity by grouping related tasks together, providing clear navigation cues, and prompting operators through complex sequences without confusion or ambiguity. This approach reduces the likelihood of errors, increases efficiency, and significantly improves operator confidence. Incorporating ergonomics thoughtfully into automation design not only improves operator well-being and comfort, but also substantially enhances productivity, safety, and long-term operational reliability.
11.2.3 Training and competency of operators and maintenance staff.
The effectiveness, safety, and reliability of industrial automation systems are ultimately dependent on the competency and skill of the people who operate and maintain them. Even the most advanced and ergonomically designed systems require personnel who understand their functions, limitations, and potential risks. Therefore, training and ongoing competency assessments are essential responsibilities for controls engineers and management. Operators should receive comprehensive training tailored to their specific roles, starting from fundamental concepts to detailed procedures. At the outset, training should thoroughly cover safe operation, including clearly demonstrated emergency response protocols. Operators need a complete understanding of emergency stop functions, safe shutdown sequences, and how to respond effectively to alarms and critical system alerts. Practical drills should reinforce this knowledge, simulating real-world scenarios to ensure operators instinctively take correct actions under pressure. Routine operational and maintenance tasks must be systematically taught, emphasizing clearly documented procedures such as startup checks, shutdown processes, basic troubleshooting steps, and minor preventative maintenance. Operators should confidently perform tasks like sensor calibration, simple fault resets, and basic component replacements where applicable. Controls engineers should collaborate closely with maintenance supervisors to create clear, accurate, and accessible maintenance documentation, such as step-by-step guides, visual aids, or video tutorials, to support operators in confidently performing first-line maintenance tasks without relying excessively on external expertise. A solid understanding of control system basics is particularly valuable, enabling operators and maintenance staff to effectively respond to faults and minimize downtime. Training should introduce personnel to key automation principles, including how PLCs operate, the role of sensors and actuators, and how data flows through the system. Operators don't need in-depth programming skills, but they must be capable of interpreting basic diagnostic information, recognizing common faults, and distinguishing hardware issues from software or network problems. Controls engineers should regularly reinforce this knowledge through scenario-based training or practical demonstrations, enhancing confidence and reducing reliance on specialist engineers for minor issues. An essential aspect of training involves teaching staff how to properly use HMIs, SCADA interfaces, and diagnostic tools. Personnel should be familiar with navigating these interfaces, interpreting alarms, understanding visualizations and trends, and identifying the necessary corrective actions quickly and accurately. Effective training incorporates practical exercises and simulations, demonstrating exactly how to navigate complex interfaces under normal and emergency conditions. Providing easily accessible reference materials, such as quick reference guides attached near operator stations, helps reinforce training, enabling swift and accurate responses to operational problems. With the increasing integration of automation systems into broader networks, cybersecurity training has become a critical component of personnel development. Controls engineers should work alongside IT specialists to ensure that operators and maintenance staff receive ongoing cybersecurity awareness training. Training sessions should clearly illustrate common cyber threats, such as phishing attacks, malware infections, and risks posed by unauthorized remote access. Staff should be taught how to recognize suspicious communications, safely handle unknown devices or software, and strictly follow organizational cybersecurity policies. Regular cybersecurity refreshers and simulated phishing exercises can reinforce awareness and significantly reduce the risk of security breaches originating from human error. Finally, periodic competency assessments and ongoing refresher training are crucial for maintaining staff skills and knowledge over time. Competency should be evaluated regularly through formal assessments, practical demonstrations, or scenario-based drills to confirm that personnel remain knowledgeable and capable of performing their duties safely and effectively. Controls engineers should collaborate with management to establish structured training schedules, ensuring that updates to machinery, software, or processes are communicated promptly and clearly to all relevant personnel. By investing continuously in comprehensive training and competence development, controls engineers help to maximize the effectiveness, safety, and operational uptime of automation systems, empowering operators and maintenance personnel to confidently maintain and manage complex industrial processes. 11.3 Sustainability and Energy Efficiency. 11.3.1 Green Automation Principles. Sustainability is increasingly becoming a critical aspect of industrial automation, and controls engineers play an essential role in achieving environmentally friendly production processes. Green automation principles involve integrating environmental considerations directly into the system design, aiming to reduce the energy footprint of automated machinery and processes while promoting responsible resource use. A core element of green automation is the specification of energy-efficient motors and drives. Controls engineers should prioritize selecting components with high energy efficiency ratings, such as IE3 or IE4, standard induction motors, or high-efficiency permanent magnet synchronous motors, PMSMS. Variable frequency drives, VFDs, provide substantial energy savings by precisely controlling motor speed according to actual load conditions. This reduces excessive energy consumption during partial load or idle conditions, which can lead to significant operational cost savings and a reduced environmental impact over time. Engineers should also consider using intelligent drive controls with real-time energy monitoring and optimization capabilities, allowing operators to continually track and refine energy performance. Automating the shutdown of idle or non-essential equipment is another fundamental approach to energy reduction. Equipment that remains operational during downtime, such as conveyors, pumps, fans, or cooling systems, can consume substantial amounts of unnecessary energy. Incorporating logic into the control system to detect inactivity, idle periods, or low load conditions allows for the automatic shutdown or throttling down of equipment, significantly reducing wasted energy. Controls engineers must carefully design these automated shutdown procedures to prevent negative impacts on production flow, machine readiness, or safety conditions. Systems should provide clear indications to operators when equipment is powered down automatically, ensuring transparency and awareness. Regenerative braking systems are increasingly adopted in automation applications, especially in motion-intensive processes like material handling, packaging lines, robotics, and automated guided vehicles, AGVs. Instead of dissipating braking energy as heat through resistors, regenerative systems convert kinetic energy back into electrical energy, feeding it back into the power grid or into local storage systems such as ultracapacitors or batteries. Controls engineers can incorporate regenerative braking into servo drives or VFDs, significantly increasing overall system efficiency, reducing electricity costs, and lowering carbon emissions. Selection and sizing of regenerative braking equipment require careful analysis of the process's motion profile to maximize the capture and reuse of otherwise lost energy. Material-efficient processes are also central to green automation principles. Controls engineers should collaborate closely with process engineers and mechanical designers to develop control strategies that minimize scrap rates, reduce raw material usage, and optimize consumables management. For instance, precise servo-driven motion control systems can significantly reduce overfeed, reject rates, or trimming waste in production processes. Similarly, intelligent vision systems integrated with control logic can rapidly identify defective products early in the process, significantly reducing waste downstream. This approach contributes directly to resource conservation, improved yield, and overall environmental sustainability. Finally, equipment design should facilitate disassembly, recycling, and reuse to support sustainable manufacturing. Controls engineers can support this by specifying modular components, clearly marked wiring, easily removable sensors, and standardized connectors, simplifying maintenance, repair, upgrading, or recycling. Designing automation systems for easy serviceability and future expansion not only extends the useful life of equipment, but also reduces waste generated by prematurely discarded or obsolete machines. Providing thorough documentation of disassembly and recycling procedures further promotes responsible equipment lifecycle management, ensuring that components can be reused, refurbished, or recycled effectively at the end of their operational life. By proactively applying these green automation principles, controls engineers directly contribute to creating more environmentally responsible industrial systems. These efforts enhance operational efficiency, reduce environmental impact, minimize energy consumption, and promote long-term sustainability in manufacturing operations. 11th point 3.2 Energy monitoring and reduction.
Monitoring and reducing energy consumption are critical aspects of modern industrial automation, both for environmental sustainability and operational cost-effectiveness. For controls engineers, achieving meaningful energy savings starts with gaining detailed visibility into how energy is consumed across machines and production processes.
A foundational step is the installation of dedicated energy meters or smart submeters at the machine, production line, or specific process level. Rather than relying solely on site-wide utility billing, localized energy meters provide granular insights into exactly where and when energy is being consumed. By measuring real-time power usage, current, voltage, and power factor at individual machines or subsystems, engineers can identify the largest energy consumers, detect inefficiencies, and set targeted energy reduction goals. Once energy consumption data is captured, integrating this data directly into existing SCADA and MES platforms enhances visibility and provides real-time actionable insights. Energy usage dashboards can clearly display current, historical, and projected consumption trends, enabling operators and engineers to quickly identify unusual patterns or spikes that indicate potential waste, faults, or inefficient processes. Integration into MES systems also aligns energy consumption data with production data, allowing analysis of energy efficiency in relation to production volumes, machine availability, and product types. Detailed analysis of energy data helps identify peak energy usage patterns, which are often associated with high utility demand charges. By understanding precisely when these peak events occur, engineers can strategically schedule machine startups, shift production workloads, or implement load management strategies to flatten demand curves. This approach not only reduces energy costs, but can also extend equipment lifespan by preventing excessive stress associated with peak demand operation. Incorporating high-efficiency components is essential to proactive energy reduction strategies. Controls engineers should prioritize specifying premium efficiency IE3 or IE4 rated motors and high-efficiency drives, which provide substantial energy savings compared to standard efficiency equipment. Likewise, specifying LED lighting within control panels, machinery enclosures, and factory lighting significantly reduces electrical load and associated heat generation, enhancing both energy efficiency and working conditions. These component upgrades, combined with intelligent controls such as automatic dimming, occupancy sensors, or scheduled lighting, further minimize energy consumption. Automated reporting and alerting features within energy monitoring systems help engineers and facility managers respond swiftly to abnormal energy usage. Automated reports can highlight unexpected consumption, deviations from historical baselines, or inefficiencies in specific equipment or processes. This not only simplifies continuous improvement efforts, but also provides clear evidence of energy savings over time, supporting corporate sustainability goals or compliance with energy regulations such as ISO 5001. Overall, effective energy monitoring and reduction require a systematic data-driven approach, integrating advanced measurement technology, intelligent analytics, strategic scheduling, and efficient equipment selection. Controls engineers who embed these strategies into system design directly contribute to significant energy savings, reduced environmental impact, and enhanced operational profitability. 11th point 3.3 Waste minimization. Minimizing waste is vital in modern automation, not only to reduce environmental impact, but also to enhance production efficiency, ensure compliance with sustainability regulations, and lower operational costs. Controls engineers play a crucial role in implementing systematic waste reduction strategies, beginning at the design stage and extending through daily operations and continuous improvement initiatives. Applying lean manufacturing principles is fundamental to waste reduction. Engineers should actively participate in optimizing processes by identifying inefficiencies, eliminating non-value-adding steps, and simplifying machine sequences. Through tools such as value stream mapping and regular Kaizen events, inefficiencies such as unnecessary waiting times, excessive transportation, redundant machine operations, and surplus inventory can be identified and systematically eliminated. This proactive approach not only reduces material waste, but also optimizes energy usage, labor costs, and overall equipment utilization. Automated quality control systems, particularly AI-driven vision inspection, significantly enhance waste minimization by detecting defects and quality deviations early in the production process. By integrating advanced machine vision systems directly into production lines, controls engineers enable immediate identification and rejection of defective products or components before they progress to downstream processes. This early intervention prevents additional processing or assembly of faulty products, drastically reducing material waste and rework costs. Additionally, automated quality checks provide detailed real-time data on defect patterns, allowing engineers to pinpoint underlying process issues and quickly implement corrective actions. Robust closed-loop control systems further reduce waste by maintaining precise process stability, reducing variability, and ensuring consistent product quality. For instance, closed-loop control of temperature, pressure, flow, or chemical dosing can significantly reduce scrap due to process variability. Controls engineers should carefully tune PID loops, employ adaptive or model-based control algorithms, and continuously monitor critical process parameters to ensure optimal performance. Maintaining stable process conditions not only improves product quality, but also minimizes raw material consumption and reduces the likelihood of defective batches that require disposal or reprocessing.
Recycling and material reuse represent further opportunities for waste minimization in automated processes. Controls engineers can incorporate design strategies such as closed-loop recycling of processed water, automated handling of reusable packaging, and intelligent sorting systems for material recovery. Implementing automated waste sorting and recycling processes directly into manufacturing lines ensures minimal waste streams and maximizes recovery of valuable resources. Additionally, integrating monitoring systems to track and report recycling rates and waste generation encourages ongoing improvement and accountability.
Finally, packaging optimization is a key area where automation can substantially reduce material usage and associated waste. By optimizing packaging processes through precise control of packaging equipment, implementing smart sensors for accurate fill measurements, and utilizing automated packaging systems that adapt dynamically to product dimensions, engineers can achieve considerable reductions in material consumption. Minimizing packaging waste not only lowers costs, but also improves environmental sustainability, helping organizations meet regulatory standards and enhance brand reputation. In summary, waste minimization involves a comprehensive, structured approach that includes lean manufacturing, automated quality control, precise closed-loop control, recycling and reuse strategies, and optimized packaging processes. Controls engineers who integrate these practices into automation designs significantly improve operational efficiency, reduce environmental impact, and ensure long-term sustainability and profitability. 11th.4 Future-proofing summary. Future-proofing industrial control systems
demands that controls engineers prioritize robust cybersecurity, intuitive usability, and environmental sustainability. Engineers must embed rigorous security practices, ensuring resilience against evolving cyber threats through layered defenses, secure remote access procedures, and adherence to standards such as IEC 62443. They should design intuitive and ergonomic operator interfaces, supported by comprehensive ongoing training programs, to enhance operational safety, reduce human error, and improve maintainability.
Additionally, environmental sustainability must be integral to system design, with engineers proactively incorporating energy-efficient technologies, robust energy monitoring and management systems, and intelligent controls to reduce energy usage and operational costs. Adopting green automation principles, such as regenerative energy recovery, use of high-efficiency motors and drives, automated shutdown procedures for idle equipment, and lean manufacturing techniques, significantly reduces waste and improves resource efficiency. Beyond these technical considerations, controls engineers must anticipate future developments by designing systems that are modular, scalable, and easily upgradable. This approach facilitates adaptation to emerging technologies like AI-driven predictive maintenance, advanced data analytics, and smart factory connectivity. Systems designed with such forward-thinking flexibility can seamlessly integrate new innovations, ensuring longevity and continued relevance. Ultimately, by thoughtfully combining strong cybersecurity practices, user-centered design, sustainable operational principles, and future-oriented adaptability, modern automation systems can reliably deliver sustained high performance. These systems will not only meet today's requirements for efficiency, safety, and environmental responsibility, but also remain robust and competitive amidst future technological and regulatory challenges. 12. All the best. Industrial automation continues to evolve, presenting new challenges and opportunities at every turn. As controls engineers, we must remain proficient not only in established practices, but also embrace emerging technologies, evolving standards, and modern safety requirements. This book began as a personal reference to help me navigate the complexities of automation engineering, but evolved into something I wish to share with the wider engineering community. My hope is that it serves you as effectively in your projects as it has served me. Throughout these chapters, we've explored the core foundations of automation, essential electrical and safety standards, practical control system programming, and effective strategies for troubleshooting, maintenance, and modernization. We have examined advanced automation concepts associated with Industry 4.0, such as IIoT, predictive maintenance, artificial intelligence, and machine learning. Importantly, we've highlighted the increasingly critical aspects of cybersecurity, human factors, and sustainability, elements that must be thoughtfully integrated into any modern engineering approach. Effective automation engineering isn't simply about solving today's problems. It involves anticipating tomorrow's challenges, staying adaptable, and continuously learning. By adopting best practices outlined in international standards, embracing secure and ergonomic design principles, and committing to sustainable engineering solutions, we position ourselves and the systems we design for long-term success. Feel free to refer back to this guide whenever you're embarking on a new project or entering a new phase of an existing one. Use it as a resource when designing systems, specifying equipment, troubleshooting faults, or upgrading legacy controls. Remember that safety, reliability, and efficiency are not isolated achievements. They result from systematic, informed, and careful engineering decisions. Ultimately, our role as controls engineers is to make automation not just possible, but practical, safe, and sustainable.